Hello to all from the DFINITY Foundation. First and foremost, we hope that you and your loved ones have stayed safe and healthy during this difficult time. As we adhere to the shelter-in-place regulations, we are grateful to DFINITY for giving us this opportunity to get together for human connection and ultimately as a reminder of our shared purpose to use the internet computer to restore the internet to its open and free roots. My name is Alexa Smith, and I manage developer partner programs here at DFINITY.
I'm Michael Hunte, and I'm the Director of Community at DFINITY. The Internet Computer is currently on a public release schedule dating back to the copper release in November of 2019 during San Francisco Blockchain Week, and the bronze release at the World Economic Forum at Davos earlier this year. The remaining milestones are the Tungsten, Sodium, and Mercury releases of the Internet Computer.
For the DFINITY team building the Internet Computer and our global community of over 250,000 followers, today is exciting because it marks the launch of our next milestone, the Tungsten release of the Internet Computer. Tungsten is especially exciting because it gives third-party developers the opportunity to gain early access to the Internet Computer and deploy infinitely scalable apps across a network of multiple data centers.
For those of you looking to build open internet services or secure tamper-proof enterprise solutions, this is the perfect opportunity to prototype your ideas in anticipation of the Mercury release of the Internet Computer. Today we have a great program lined up, from discussions with industry experts including Chris Dixon from Andreessen Horowitz, Olaf Carlson-Wee from Polychain Capital, and Professor Dan Benet from Stanford University, to insights from third-party developers already building on the Internet Computer, and lots of demos. Most excitingly, you'll have the opportunity to submit questions throughout our event today into the chat to be answered during our live AMA with founder and chief scientist Dominic Williams.
Now we'll be handing things over to Dom to kick off our Tungsten launch event, which will be followed by 2 quick teasers of demos that we'll showcase later today. Over to you, Dom.
Welcome and thank you so much for attending the DFINITY Foundation's Tungsten launch event for the Internet Computer project. I'm Dominic Williams, the project's founder and chief scientist. Over the past 4 decades, network speeds have increased more than 400,000 times, while the memory inside personal computers has grown 1 million times. It's natural to ask whether the way we build software and services using computers has improved as much. We think you know the answer. The legacy stack has been stuck for years. Our solution is radical, and it's called the Internet Computer. The Internet Computer is an extension of the Internet that is created using a blockchain computer protocol called ICP that weaves together compute capacity from data centers around the world. The Internet Computer upgrades the Internet so that it can natively host software systems and internet services such as DeFi, social media, streaming, and games, transforming the internet into the final compute platform that humanity builds on, as well as the network that connects us all. Internet computer developers don't need the old stack. They don't need big tech's cloud services. They don't need traditional components like web servers, databases, firewalls, and CDNs. And they don't need a blockchain for security and autonomy. They simply upload reimagined, interoperable software units called canisters into the Internet Computer's open protocols, where they run in cyberspace within an environment that's tamper-proof, unstoppable, fast, and has limitless capacity. Tungsten is the third of 5 public milestones culminating in the Internet Computer finally spinning out as part of the public internet later this year. The first milestone, Copper, was released in November last year and provided the world with a software development kit and a new computer language called Motoko that has enabled a growing army of Internet Computer enthusiasts to build some really impressive systems and services that will run on the Internet Computer. The second milestone, Bronze, was demonstrated at Davos at the World Economic Forum, January 2020 this year. We demonstrated a new kind of open internet service that can be powered by the Internet Computer. In this case, a social network for professional profiles called Linked Up that was running off the Internet Computer in incubation. Tungsten is an even greater leap forward. I'm pleased to announce that the internet computer is now running across multiple data centers worldwide, and that we're throwing it open to developers, teams, and projects like yours that are building interesting things using the expanding range of developer tools available. For the first time, developers will be able to run the systems and services they have been building off the internet computer for themselves. To celebrate Tungsten, we brought in some very eminent guests for you from fields such as academia and venture capital, who will talk about the evolution of the internet and the tremendous opportunities that it is creating for developers, entrepreneurs, investors, and enterprises alike. After discussions with our eminent guests, we'll progress to hands-on demonstrations of how to build systems and services on the internet computer that are broad enough even for those who don't code to get a handle on what becomes possible when the internet is transformed into a limitless public supercomputer that the world shares.
Hi, I'm Larsen, engineering lead on the SDK team here at DFINITY. What I'm about to show you is a fully working chess engine running on the internet computer. This is a very simple front end made in JavaScript that starts a new game and interacts with the canister running on the internet computer. Every move I do triggers the engine to calculate the next move. You can see the moves here showing up in the logs. The canister itself is made in Rust using existing libraries. It uses orthogonal persistence, so you can come back to your game in a month or two and the state would be the same. It does not require Motoko or any other languages. Anything that can target WebAssembly can be used to build canisters running on the internet computer. You could imagine this being a game against another person on the internet, or multiple people voting for the next move against a chess master. Or it could be an entirely different game, like a card game, or maybe a lottery system. Since nobody owns the canister or the game, nobody can mess with it. This is just a sneak peek. Stay tuned for the full version later in the event. I'm looking forward to show you all how this was implemented. Thank you.
Hi, I'm Stanley Jones. I'm an engineering manager here at DFINITY for the developer experience teams. In addition to improving your productivity with tools like the Canister SDK and the Motoko programming language, the developer experience team builds example applications to demonstrate the benefits of the platform and assess what is easy, what is hard, and what's still impossible. For our bronze milestone last quarter, we showed you how simple, fast, and secure you can make a full-stack web app. We built a social network for professional connections that we called Linked Up, and everything ran on the internet computer. You didn't need a web server, a database, a CDN, or any of the other complexities that you've come to accept as inevitable in legacy software engineering. And Linked Up surprised us with how fast it was, serving up profile pages in less than 20 milliseconds. It made us wonder what else was possible on the internet computer. So today I'd like to show you our latest example app. It is a scalable, decentralized video sharing app that lets people stream and share videos from their mobile device directly onto the internet. It's great for silly videos, dance videos, cat videos, or really the ultimate purpose of the internet itself, silly dancing cat videos. We call it CanCan. I'll go a little deeper into how it works later. But for now, let's just watch some videos streamed straight from the internet computer. Okay, thanks. I will see you later for a technical deep dive.
Thanks to DFINITY senior engineer Hans Larsen and engineering manager Stanley Jones for the teasers around autonomous chess and CanCan, a scalable, decentralized video sharing app built on the Internet Computer.
Next up, we have Dominic Williams to talk through the roadmap for the Internet Computer and where the Tungsten release fits into the public release schedule. Then we'll have two very exciting conversations. The first conversation, titled Billions of Dollars Waiting to Invest in the Open Web, will feature Olaf Carlson-Wee from Polychain Capital and Bettina Warburg from Warburg Serres Investments. It'll be moderated by our very own COO, Artia Moghbel. The second conversation is titled Building on the Internet Computer, and will showcase third-party developers Rick Porter and David Fawn from the Origin project, as well as DFINITY senior engineer Enzo Haussecker, who have already been building on the Internet Computer. This conversation will be moderated by our very own Alexa Smith. So without further ado, please give a warm welcome to Dominic Williams.
About 40 years ago, the modern internet came into being, and it has played the role of global public network in a remarkably stable way. We still use the TCP/IP protocols to connect anything and everything. However, if we want to build a website, internet service, enterprise system, or other system connected to the internet, we need to use this proprietary legacy stack. Typically, we start off with a cloud service from big tech, such as AWS, possibly add in other services such as CDNs, and then combine traditional building blocks such as databases, web servers, application servers, and frameworks like Kubernetes. The problem is that the complexity overhead is enormous. And we build these big Rube Goldberg machines that are insecure by default. So we have to protect them with things like firewalls. But if just one of those components is misconfigured or gets out of date, or we write some bad code, hackers can hop the firewall and create havoc. On top of that, it's all too easy to get locked into the components we're using, and the thousands of vendors involved in the legacy stack play captive customer games. All of this drives a worldwide IT spend of a staggering $3.9 trillion a year. Moreover, this stack can't support autonomous code, which is what we need to reinvent the internet ecosystem. Over time, the legacy stack has grown to include popular internet services from mega monopolies and the user data and relationships that they control. It's time for a reboot of the internet. Luckily, a new paradigm is emerging, and a new transition is upon us. The Internet Computer upgrades the public internet so that it provides not just global connectivity, but also a revolutionary shared computer. This transformation of the internet is achieved through a new open protocol called ICP, or Internet Computer Protocol. Let's talk some more about it. The Internet Computer is a replacement for the proprietary legacy stack. It's created by independent data centers running ICP, which forms a new kind of blockchain computer. This has unbounded capacity and delivers performance that rivals the traditional cloud. The Internet Computer reimagines software as interoperable compute units called canisters. Software canisters are an evolution of smart contracts. They consist of a bundle of WebAssembly bytecode and the memory in which that bytecode runs. Just like smart contracts, canisters are tamper-proof and unstoppable. However, a key difference is that they are also scalable and parallelizable. Canisters also run at web speed and are highly efficient. As you would expect, they are open and interoperable. That means that if you create a canister using the Rust programming language and share some functions with me, and I create a canister using the Motoko programming language, my Motoko code can call your functions directly. The Internet Computer is tremendously powerful. You can use it to build just about anything without AWS servers, CDNs, databases, firewalls, and so on. You can use it to build websites, open internet services, enterprise systems, pan-industry systems, and you can use it for all of those classic applications of smart contracts like DeFi. You can create new systems and services on the Internet Computer in two simple steps. In the first step, you write code in any programming language that compiles down to a WebAssembly canister, such as Rust or Motoko. In the second step, you simply upload the canisters that you've created to the Internet Computer using its open protocols, and that's it. The Internet Computer enables you to build directly on the Internet itself. No big tech, no legacy building blocks, no cloud services. Because of the way canisters work, you won't need a database server. Canisters can serve user experiences directly into web browsers, so you won't need a web server. Because the Internet Computer is a native edge architecture, you won't need a content distribution network to speed up your systems and services. You won't need a DNS service, because the Internet Computer is a giant DNS server. And you won't need firewalls because your canisters run within a tamper-proof environment. The Internet Computer enables a completely new way of doing things. But the Internet Computer isn't just about providing better ways of doing things that we did before. It's also about providing ways to do things that we couldn't do before, such as building open internet services, using autonomous software that runs without an owner, like a person or corporation, that can share special APIs that cannot be revoked, enabling service composability through the trustless sharing of user data and functionality, and which can be controlled and managed entirely using transparent, open, tokenized governance systems. It's also about providing entrepreneurs with new revenue and fundraising models, and ways to generate stronger mutualized network effects that can beat out monopolistic incumbents. The Internet Computer is about powering a rebuild of our internet ecosystem in open form and enabling more collaboration, innovation, and dynamism. And we hope you'll join us leading this movement.
Hey everyone, thanks for joining our panel. I'm Artia, COO at DFINITY, and I'm really excited to be joined today by Bettina Warburg from Warburg Serres Investments and Olaf Carlson-Wee from Polychain Capital to chat about the billions of dollars in capital waiting to be invested in the open web. First off, thank you Bettina, thank you Olaf for joining me. My plan in conversation today is to dive a little bit deeper into your experiences as investors in the decentralized web, your investment theses in the space, and what you look for in potential funding opportunities on the Internet Computer. So to kick things off, Bettina, Olaf, mind introing yourselves?
I'm Bettina Warburg, managing partner of Warburg Serres Investments and Animal Ventures. We're a private equity firm focused on investing in Web3 technologies.
Hey, Artia, thanks for having me. My name is Olaf Carlson-Wee. I'm the founder of Polychain Capital, and we invest in the entire blockchain and crypto universe.
Great. Thank you both. And to give our audience a bit more perspective, the objective of this segment is to give developers and entrepreneurs the confidence that there's capital waiting to be deployed in Web3 technologies like open internet services. At DFINITY, we've been really excited to see the massive boom of innovation around the decentralized web and are seeing headlines appear in higher frequency around rebooting the web, but also how big tech has been an obstacle for innovation. So I'd love to open up the discussion to either of you to chat about why the current state of the internet and why the control of big tech is a detriment to innovation in the space. The Wall Street Journal, the New York Times, and a handful of other publications have already covered this topic, as well as some major politicians in the current political race. So would love to kick things off by getting your perspective on that.
Yeah, absolutely. I'm happy to kind of start the conversation. So, the web used to be a system whereby you would sort of go directly to original content hosted by, various smaller websites. Over the course of the sort of mid-2000s, we saw the sort of platformization of the web. And now really all of the content that you see on the web is hosted on a series of very, very large platforms. And these platforms are owned and operated by the world's largest corporations by market capitalization. So I think that there is a sort of problem when you're a developer trying to build useful services today, which is that you're building on somebody else's proprietary platform. A lot of people call this sort of building on sand. You just don't have a solid base because the platform that you're building on is really owned by somebody else. And for that reason, your scale is limited, your ability to control your own destiny is limited, and of course, your ability to compete with that underlying platform is obviously going to be hindered by the owners and operators of that platform. So one of the big ideas behind open web services is that developers can compose on a completely open programmable system that looks and feels very similar to the internet protocol itself. And when you compose on that sort of open web platform, you can't be censored. No underlying corporation or jurisdiction has sort of control on that platform or ability to censor what is created there. And so there's a couple big important breakthroughs to me for that. The first is that you're finally going to be able to see people build these programmable web services that can't be shut down by the underlying platforms they're building on.
Yeah, I would totally echo Olaf's point there on, we're definitely becoming increasingly aware of platform risk and the kinds of examples he's citing where if you have built or the things that could have been built on top of the platforms that exist today, whether it's the App Store or Facebook or Twitter or any of the other platforms we sort of know, those are actually risk disclosures in public filings often. Even if you've built on, for instance, in Lyft's IPO, they had to disclose that they actually see their reliance on Amazon Web Services as a potential risk because they're using a third-party provider and could face downtime or anything else due to that. So I do think this is a major issue in terms of our existing sort of digital architecture. Another one, though, that's becoming increasingly obvious is just that the business model of our internet is advertising at the end of the day. And so what we're asking different entrepreneurs to innovate on if they're building in today's world is just some better way to advertise to users, which is kind of an inherent friction and an unfortunate relationship for the user experience. So what Web3 really promises and what open web services promises for developers in particular, I think, is actually asking entrepreneurs and developers to be creative and build models for their businesses that aren't entirely around optimizing for ad revenue and ad dollars, and instead, optimizing for something totally different, a different way to make money. I think that's exactly as Olaf's describing, we're going to see phenomenally different kinds of businesses emerge that aren't sort of hamstrung by this one business model of the internet that's been sort of our reality over the last several decades.
Yeah, and that advertising to end users, it really means that the user is you're providing of data to these massive centralized web platforms really is their business model, and so you as a user aren't really sharing in any value accrual or value creation from these web services, even though, the only reason anyone uses Facebook or Twitter, any of these social media systems like LinkedIn or marketplaces like eBay or Etsy, the value in those systems stems from your interaction with other users on those big centralized web platforms. Yet there's an immense amount of value extracted by those centralized web platforms in all of those underlying interactions between the users. One of the very promising ideas behind open web services is user-owned platforms. So you could imagine a world where the users of, say, Uber or the users of Etsy actually share in the upside and kind of collectively own that underlying web platform. And I think it's kind of a radical new idea that you have to squint a little bit to see what that would look like. But I do think community-owned applications are going to be a huge part of the future and dramatically change the way we think about the business model of the internet.
So you both just touched on some really interesting points there that I'd love to unpack. The first is around platform risk, and I think, Bettina, it was you that mentioned that in the Lyft S1 filing, there was actually mention of Amazon Web Services as being a significant and potentially existential threat to Lyft going forward before the company went public. But I actually think if you look at the past year or so of tech IPO filings, the vast majority of them actually mention platform risks as one of the major risks for the company post-IPO. So would love to actually sidestep into one of the topics you brought up, Olaf, to discuss the difference between proprietary infrastructure and a protocol. Would you mind expanding on that a bit?
Yeah, absolutely. So, when you're building on these proprietary infrastructures, you're very limited in both your ability to scale an application because the underlying infrastructure is proprietary, owned by a third party, and they basically control your fate, so to speak. And I think like a very high profile case where this went wrong is, for example, Zynga, which basically built Farmville, one of the most popular games of all time, but they built it on the Facebook API. And when Facebook restricted their ability to use that API, it obviously had a dramatically negative effect on Zynga's ability to build a sustainable business. As I said before, they were basically building on sand, right? They weren't really building on a solid foundation. I think that one of the really interesting kind of early product market fit use cases we've seen elsewhere in the blockchain ecosystem is this concept of DeFi, or decentralized finance. A lot of these ideas, you really have to take advantage of sort of the native properties of the underlying system you're building on. And I think in the early internet, Encyclopedia Britannica on the internet was probably a pretty obvious idea, right? Great distribution, infinite reproducibility. But I think Wikipedia was not an obvious idea. And so one of the things that, we at Polychain, and I know many others in the investment landscape are excited about, are kind of novel business models that are, uniquely enabled by the features of these new Web3 platforms. So it's not taking the Web 2 model and moving it onto Web 3, the way that Encyclopedia Britannica moving onto the internet would be. It's really working on building that native business model that's a completely sort of new paradigm that's uniquely enabled by features of this underlying new tech stack.
I think that's a really good point, actually. We often see with new technology frameworks, we just take the old and sort of slap it on the new, right? We saw that with things like radio. Like people who used to do radio, once TV came out, they just did radio on TV and didn't totally utilize the affordances of the technology or the format to its benefit. So it's entirely correct that, we're maybe just scratching the surface of the kinds of different approaches, different paradigm that's going to be possible. And I would argue one of the sort of core reasons we'll see different types of business models emerge is also around this idea that because we're talking about open source, you can really see what happens when standards come into sort of the community, right? So even things like ERC20, once that emerged, an entire multitude of different kinds of businesses, even Coinbase, were possible just by way of having a standard and a way to sort of coordinate in a new way with tokens. So I think there's really interesting opportunities where we're going to see standards emerge that also allow for whole new economies to flourish, whole new marketplaces to flourish that wouldn't have been possible when you're talking about these more proprietary infrastructure backgrounds.
Great points. Thank you both. One question I'm often asked about is around the paradigm shift with the open web, one that allows developers and entrepreneurs to think through more unique business models. I'm curious if either of you can chat about what some of the native mechanics are in a protocol versus building on a proprietary platform like Facebook that would enable new business models. I'm personally looking for a counterexample to how Zynga built their entire company on Facebook. So Olaf, you already mentioned user-owned applications. One obvious native feature of a protocol is the native payment mechanism as well. So can either of you, Bettina, Olaf, outline some of the native mechanics that are unique to the open web that developers and entrepreneurs listening to this panel can start thinking about?
One big trend that I think is going to be much bigger when you can compose more expressive, smart contract logic that, again, is not limited to financial or mathematical logic, but actually can interact with images, video, text, and so developers can build a more kind of expressive user experience that isn't limited to just financial logic, the way that existing platforms out there today basically are limited to that financial logic. So I think the one of the big trends is this idea of a financial service that's embedded in a smart contract. And the reason that it's important to embed it in a smart contract is that it's not based on any sort of proprietary server. It's not owned by any business. It's not based in any jurisdiction. It's rather totally native to the internet. And that smart contract might have, a native financial service like trade execution, or a lending system, or an escrow system. And then there's a series of token holders that basically represent the governors of that smart contract system. So they have the ability to vote on upgrades and changes to that underlying smart contract logic. In return for sort of governing this system, they actually accrue value from that underlying system.
One of the things we're particularly interested in when we start to imagine what's coming next is concepts like, stateful virtual worlds. The entire gaming industry is probably going to change when we start to understand what it really means to participate in a virtual world that has a shared reality that everybody participates in at the same time. I think that's gotten a lot clearer to people, even amid things like our current, pandemic globally. People are understanding what the future might look like when virtual worlds are, the basis of multiple economies. And I think that's something that, whether you talk about blockchain computers or gaming or anything else, it's sort of, at the end of the day, what we care about is also our user experience and what our world is going to look and feel like. And that's, I think, what's going to change significantly is when these technologies intersect, you'll actually see a lot of possibility in terms of both marrying that computing and incentive model architecture with new user experiences. And I think, we're just at the cusp of the kinds of businesses that are going to emerge when we have virtual worlds that are stateful.
So I'd love to continue down this thread of talking about the boom of innovation we see on the open web. And as both of you know, starting today, DFINITY will welcome third-party developers to the Internet Computer in the lead up to our public network launch. So I guess I'm curious, if you were in the position of a developer or entrepreneur, what are some of the first mover advantages you would take into account or think about when considering building on a protocol like the Internet Computer?
I think that the first movers in various categories, whether it's sort of exchange and financial services, or whether it's just getting the most popular stablecoin protocol, which is pegged to, say, the US dollar or another fiat currency, or getting the most popular and liquid lending protocol. The first movers in these systems, these financial services have very strong network effects, primarily around liquidity. So if you can build an early wedge and the category is going to grow by 100 times, that's usually the best way to build a great business, is to get in early when it is small and not very competitive, and there's frankly not very much money to be made, but then have a clear thesis about how that category is going to grow and expand. And when that category grows and expands by 100 times, suddenly your 70% market share is worth a lot, even though when you kind of built that market share, it wasn't very competitive and it wasn't worth very much. So I think getting in early and trying to capture market share in network effects businesses has been empirically, I think, one of the most reliable ways to build kind of multi-hundred million or billion-dollar businesses, both inside and outside the sort of larger blockchain and crypto ecosystem.
I think additionally, the reality is this is a fast-paced area for innovation, and the earlier you're in, the earlier you're learning. I think part of what Olaf and I are describing in terms of the new business models is this idea that, we don't know all of the business models that are going to emerge when you have, virtual machines in the cloud that anybody can build applications on top of. It's a new thing. And so I think the idea that you're going to come up with it without getting your hands dirty is just usually doesn't bear out. So being able to be early and learn as quickly as possible what works, what doesn't, how to best take advantage of this new architecture, I think puts any entrepreneur or developer far ahead of the pack. And right now that's the advantage you want, absolutely, whether it's in fundraising or, in driving user adoption eventually.
Yeah, and that's a really good point, Bettina. So far we've talked a lot about being a first mover. We've talked about getting creative around business models. But like you just mentioned, Bettina, user adoption is probably just as important. So I'm curious, do either of you have thoughts on not just unique business models, but also unique growth models for someone building on the open web?
What's exciting about the open web and this new architecture is, in part, the ability to do combinatorial innovation. I mean, that's kind of what we've been describing as one of the downsides or sort of stifling elements of our current Web 2 architecture is, we call it platform risk, but it's also that you really don't have this mechanism of taking value you've created in one place and making it usable somewhere else. And so the kinds of businesses and incentive structures that you can start to play with when, whether it's a virtual sword in a game or, something else that you've accrued value in, the fact that you could either build a business on top of that, and change the economic value from being locked into just one business is pretty remarkable. I mean, I think that's where we start to see, from Warburg Serres Investments perspective, we're really focused on protocols, the sort of core architecture of these networks today. And then above that, broadly middleware, but the tools and services that are going to make it easier to do things like build totally combinatorial businesses. So I think we're from the application standpoint, we're still hopeful that that people are going to come up with models we haven't even imagined yet, but we're going to need some of that more infrastructure and middleware to really open up the possibility for devs to be able to use these environments as effectively as possible.
And yeah, it really is remarkable to think about what is possible and what can be created when every single one of these open internet services is sort of remixable and reusable by any other developer in the world in a totally permissionless manner. And this is like, once you have a video game items, right, embedded in that system where a sword or a shield or an avatar is represented in this underlying, kind of internet computer data structure, now somebody else can actually interact with those in-game items in a way that the initial game developers don't even have the ability to stop. So now I can build, let's say you have your Fortnite avatar, a different independent game studio can say, hey, actually you can use all the attributes of your Fortnite avatar in our game. And, the developers of Fortnite in that example couldn't even say no to that. And so you're going to have a much more additive feeling to this open system, right? Where everyone is sort of building one big experience together that's sort of better for everyone, rather than a bit more what you have today, which is these extractive competitive platforms basically attempting to monopolize and shut down competition that's trying to interact with their closed APIs.
Another thing we haven't touched on yet is the idea that, we can say, the business models will be radically different, but we also have to conceive of the fact that the users will be radically different. A lot of the value for this kind of future is unlocking machines as an entirely new consumer class. And I don't think people often, make that switch when they talk about the open web, because a lot of us have our own values tied to these concepts of open and sort of returning to the architecture we imagined for the internet, and that the crafters of the ARPANET and other things imagined maybe. But the reality is we're in a world where, we have 50 billion connected devices. We're trying to automate different enterprises at, multiple levels. We have supply chains that should be programmatic by now, but aren't, and often aren't because they're sort of constructed in a way where you have multiple parties that don't share the same reality. So I think, there is a whole different realm here that isn't just about sort of incremental improvement of business, but is also a paradigm shift in terms of actually architecting things that are meant for machines as users. And that's going to be a whole separate category of innovation that I think we haven't seen occur on our existing internet architecture because it doesn't support payments and verification and all of these things that stateful and persistent virtual machines do.
Right. So you both bring up great points. To your point, Bettina, you described the Rube Goldberg machine that we often talk about internally to describe the existing tech stack. You have a lot of different components, whether it's databases, web servers, firewalls that are operated by different companies that are all protective of their own portion of the stack. And to your point, Olaf, you talk about interoperability, which is one of the key features of the internet computer, which basically means when you get access to an API, it can't be revoked. Which also means network effects can't be stopped. So want to shift gears a bit, and what I'm really excited to chat about and what I think a lot of our viewers are going to be excited to hear about is how do they get funding? I know between the two of you alone, we're talking about over $1 billion in assets under management. So I want to ask both of you, what are some of the decentralized applications or services that you want to see built, and what is ultimately fundable?
We're starting to see really cool middleware projects emerge that make it easier to build on these exciting computing platforms. So I think, from our perspective as investors, we're constantly scouting for the companies that are, have the right worldview, are looking at this space, trying to make sense of, which networks have an architecture that's going to allow their business to do the best it can, and really sort of leverage this up the stack kind of investment wave cycle.
Yeah, we're really looking for radical new business models that are principled and based on the properties of the underlying technologies that those businesses are being built on. So I am way more excited to fund the service or product that is sort of native to the new system, rather than what feels like a porting of an application from Web 2 to Web 3. One of the categories that I'm personally very excited about are sometimes what I've called internet sovereign corporations. And these are where there's kind of a business model or a value accrual system, but it's not really going to a legal entity, but rather to a series of token holders based entirely on the internet. And so the entire business model, the governance of that business, the value accrual of that business, all happens on the internet. And there isn't really a legal entity or individual geography or jurisdiction in which that business is limited. So this is, those types of businesses are obviously uniquely enabled, right, by this new tech stack. You really can't do that today without these, blockchain or internet computer type systems. And so that's a category that I'm very excited to invest a lot of capital in.
Thank you both. Appreciate you covering more around your investment theses and what you're looking for in the space. So to dive a little bit deeper, I'd love to hear more specifically about what you want to see built on the internet computer that you think is fundable.
Yeah, for me, I want to invest in more of these internet sovereign corporations where you have an underlying financial service or web application that's actually owned by a series of sort of token holders, and all of the value accrual and web service and everything is all native to the internet and the underlying internet computer. And there's no dependence on a specific geography or legal jurisdiction or legal entity in which that operates. So I think that, to be more concrete, for example, a very simple social media application. Think like a Twitter 1.0 kind of application. But instead of hosting that on a proprietary server with a business in a specific jurisdiction, really just having Twitter, the protocol, right? That's open and accessible. I think that's, again, though, limiting, the way I'm talking about it is limited to the framework of thinking about what was built with Web 2, right? So what's really even more interesting than Twitter, the protocol, to me, is the native business that wasn't possible on the Web 2 system, much in the way that Twitter wasn't possible before the internet, right? There was no sort of offline version of Twitter. And I know that sounds silly, but really in the early days of the internet, there was a lot of porting, like my phone book, onto the internet, right? And really what ultimately ended up working were internet native platforms, right? That were uniquely enabled by the features of the internet. And so while Twitter, the protocol, is an interesting concept, and I would be interested in investing in that type of thing, really what's more exciting to me is the applications that are uniquely enabled by the Web3 architecture.
I think additionally, I would turn it to you, Artia, and say, what do you need built on top of DFINITY? Because those are the things we're interested in investing in. As we pursue investments up these tech stacks, that's kind of, the next thing. What is going to be the most useful for your community?
That's a great question. Ultimately, the internet computer is a general purpose compute platform, and we're all really excited to see how creative the community can get with some of the native features and mechanics of the internet computer when they're building applications. I think one salient example from the past that can actually be an analog for the future is the way Uber couldn't have existed without the shift to mobile. I think entrepreneurs now should be thinking about what couldn't have existed prior to the advent of the open web and platforms like the internet computer. In terms of actual apps, there's a long answer and a short answer to your question, Bettina. I think the short answer is that our research and development team has done a really good job of building sample apps that we publish to GitHub for the community to not only learn how to use DFINITY and Rust and Motoko and other programming languages we'll be supporting on the internet computer, but also to encourage them to take those ideas, learn about some of the native features of the internet computer, and continue building where the code left off. And there are both consumer and enterprise use cases in those repos. So just to wrap things up, given we're short on time, we've talked about business models, we've talked about growth models, we've talked about your investment theses and what you're looking to fund. Ultimately, though, what are the best ways developers, entrepreneurs, enthusiasts can get connected with you both if they're interested in building a business and getting funding?
Me and my whole team are very much on the internet. So just talk to us. Happy to take a cold email, find me in any forum on the internet. I just think this whole industry is very internet first, and so we're out here.
I'm going to make a plug for not using big tech, so better to contact us from our website, warburgserres.com. You can email us hello@warburgserres.com or at animalventures.com.
Great. Thank you both for participating.
Yeah, thanks for having us, Artia.
Can't wait to see what everybody builds on top of DFINITY. So we're really excited for the launch of Tungsten and looking forward to staying in touch.
Thanks all.
Hi everyone, my name's Alexa Smith, and I manage our Developer Partner Program here at DFINITY. I'm really excited for the next panel today, which is focused on building solutions on the internet computer. This will be a more technical panel, and we have 3 developers joining us today. Enzo Haussecker, who's a senior software developer at DFINITY, and we also are joined by Rick Porter and David Fan, 2 veterans in the blockchain space and software developers at the Origin project, which is focused on building solutions for the internet computer. So today we're going to be focusing on what it's like to be a developer for the internet computer. So we'll be hearing from Enzo, Rick, and David about some of the projects that they've worked on, as well as how you get started with building canisters and building applications and enterprise solutions for the internet computer. We'll also focus a bit on how the architecture of applications is turned on its head with the internet computer, and how the simplicity of building apps is really a major benefit for developers. So we're really excited to dig in with you today, and we hope that this conversation will be enlightening to developers who are just getting started and they want to know what's possible with the internet computer. So to start us off today, Enzo, Dom spoke earlier today about how deploying software to the internet computer is super easy. So developers can basically just write their code and directly deploy it. Is that really the case? Is it really that easy?
Yeah, I think that's a totally fair characterization. One of the things that DFINITY makes it really easy for is for you as a developer to really focus on where you add value, which is typically in defining your business logic. Developers, at least in my experience, don't want to deal with replication and failover and database administration and the likes, but really just to focus on where they feel like they're making the most contribution. So one of the things I think that's really cool is that developers can really focus on where it is that they're adding value. Developers don't really add value through replication and failover and database administration and all these and the likes. This is for a long time, this has just been things that we have had to deal with in software development. And one of the things that a lot of developers are looking for is a platform where they get all this stuff for free and they can really focus on their business logic. Defining that business logic in code, being able to compile that code down to WebAssembly and deploy that WebAssembly binary on the IC platform.
That's great. Thanks so much, Enzo. And Rick, if we could switch over to you for a moment. You have a ton of experience developing enterprise platforms, consumer products, both in the centralized and decentralized space. And I would love for you to share a little bit about what kind of existing computer science paradigms or principles does the internet computer feel like? So as a developer kind of entering in for the first time, what would you compare this experience to?
Yeah, it feels a lot like microservice architecture, which pretty sure it is. And you have that ability to actually spin up all these independent canisters or services that have their own kind of independent function that they must take care of. And you can string them all together through different types of inter-canister communication. But you can also do monolithic architecture with inside of DFINITY. You can take an entire application and put it in one single canister and completely manage it through that process, or you can start breaking it down into its individual components.
Great. And actually, David, I would love to switch over to you, building on what Rick just said. So you have some experience building decentralized applications, and one of the more challenging aspects of this is actually building a front end and a great user experience. I'm wondering if you could walk us through sort of the past experience of building front ends for decentralized applications and how this new canister architecture in the internet computer has enabled you to build better front ends.
So in terms of front-end development, you usually develop it in JavaScript. So you will call your SLM provider using Web3.js. So for example, I was using Guess and Infura. And to host your dApps, you were using maybe a traditional hosting or maybe IPFS or Swarm. And now in this new paradigm on DFINITY, we got the DFINITY starter package that is based on Webpack, and you can develop your front end using any JavaScript or TypeScript framework. So you can use Vue or React. So I personally already developed some DFINITY dApps using Vue and Vuetify. And in order to call the canisters, basically you just import the canister module that is generated by the Candid compiler, and you just call the functions of your canister with a similar syntax to Motoko. Once this canister code is deployed on the internet computer, you got the front-end code that is bundled, and it's hosted on this internet computer too. So I found the overall developer experience slightly better than using this Ethereum Web3.js. Yeah.
That's great. Thanks, David. Switching back to you for a second, Rick. I know that you and I have had some conversations around how the internet computer really takes this three-tier traditional architecture and kind of turns it on its head. And that, as a software developer, you've been really excited to see sort of how that traditional three tiers of kind of UX, client-facing layer, the database layer, and the business logic layer are all sort of changed in this new paradigm. I wanted to see if you could maybe share an example with us from your work with the Origin project that reflects sort of what this new architecture looks like.
Yeah, for sure. So Origin is kind of acting as an ERP for watches, right? Where you have all this data, we have all this watches stored inside of the Origin, these Origin canisters. And you have this traditional, you could think about it as a traditional database where you have your schema, and the watches themselves follow this kind of paradigm where they're all stored within inside of this schema and following all the different standards where they have all their different relationships. The company that the watch belongs to, the winding mechanism that the watch has, and as you hear these different components, you can start visualizing the schema itself for the project. And we have this data representation within inside of the Origin canister itself, as described, so that when data is actually coming in, it is actually fit within, it's transformed to fit within inside of this data model. But if you took this data model out of DFINITY and you just wrote it down, it would, in some sort of pseudocode, it would appear to be just like any other traditional data system that you would see. So this is kind of the database of the system. It's stored within inside of the canister, and there's no need to have some sort of like ORM in place, object relational mapping, or any type of communication to a database, because of the orthogonal persistence itself. All the information forever exists within inside of this canister. So you're really just creating CRUD for the canisters themselves: create, read, updates, deletes. And obviously you'll have a lot of different types of sorting and listing functions, or some sort of map reduce that is returned to the front end. But abstractly, you just have that CRUD, and all the API itself, when communicating with the Origin canister, takes in each one of these requests and each one of these actions, and your code within inside of DFINITY handles it. And it's updating objects in memory. It's not, creating a transaction for a database, creating your SQL statement and performing an insert. By updating the object within memory, it's persisted within inside of the canister at the end of the transaction. And so when working with front-end technology like what David described, you have your front end, which we use Vue.js, that just calls these endpoints that are exposed by the actor within inside of the DFINITY canister to perform these very specific types of actions.
So we heard how the internet computer can really simplify the architecture of applications. We also heard from David on how the development experience is much easier for front end. But one of the major challenges still facing us in the decentralized space is this issue of scalability. And we saw a preview today of the app that you'll see more of later today, CanCan, which is a decentralized, scalable video sharing app. And we're lucky to have Enzo with us today, who is one of the key developers behind CanCan. Enzo, I was hoping you could share with us a few of the scalability solutions that were considered for CanCan and how these scalable applications are really made possible on the internet computer.
Great question. So I would say scalability is really multifaceted, and perhaps some of the most important points to focus on really there are really thinking about scalability from the perspective of the end user, and what are the specific use cases that they have that they're able to sort of get for free from the platform. So when I think about these types of use cases, I mostly think about scalability just in terms of storage, and I'm happy to speak to other points as well. But in the context of storage, an individual canister itself is just a WebAssembly module. It has sort of this, this linear memory section associated with it, which can grow up to 4 gigabytes in size. And then beyond that, you do actually need to think about distributing your data across possibly multiple canisters. And that's actually not a limitation that's comes from us. That's a limitation that comes from the WebAssembly specification itself. So even if you're whether you're running WebAssembly on the IC platform or whether you're running WebAssembly in the browser, you do have that same limitation. So in that context, the canisters themselves, you have the ability to sort of start off small, maybe a canister. I think the initial size of that memory is something like 64 kilobytes, and then you can always grow that to some offset of the WebAssembly page size, which is also 64 kilobytes, but never really exceeding more than 4 gigabytes, with that limitation there being the upper bound. So there's a couple of different strategies that you could take to distribute data across multiple canisters. One of the things that I worked on for a video streaming application was just implementing a distributed hash table. So that is taking a hash table and really splitting the contents of the data across multiple nodes or canisters in this case. And we did this just because DHTs have been around for a long time. There are several popular implementations to choose from: Chord, Kademlia, Pastry, Tapestry. And a lot of these implementations, they do have some common themes associated with them. There's usually some notion of key space partitioning, which splits ownership of data amongst participating nodes or canisters again in this case. And then also some notion of an overlay network, which allows nodes to find the owner of a given key. So an important thing to note there, though, is that the internet computer doesn't actually have network interfaces associated with it. It has rather canister interfaces. So any notion of an overlay network must be a virtual construct, of course. But the WebAssembly-based virtual machine that's provided by the IC platform implements a set of host functions that allow canisters to sort of call one another. So you can think about these types of overlay networks that you would typically have running for over TCP/IP for a more traditional DHT, just operating via canister calls in DFINITY. And so with that, basically what we were able to do was take video files, chop them up into sort of video fragment files and together with a manifest file, and just take all that data and write it into this key value store that was distributed across multiple canisters, and then be able to serve that data on demand to users who were consuming content. So the use case there is that if a user wants to sort of stream a video, that they're able to sort of load a web interface, and sort of as they're consuming content, be able to fetch in these video fragment files on demand and have them display and render in their browser. And to do that in a way that this data can sort of persist with this type of backend here, and the end developer not really having to think too hard about building the application at all. In fact, one of the really cool things I'd say about this specific application that I got to work on was really just the fact that the way in which the front end and back end were able to be separated were really able to be just treated as two entirely distinct entities.
Yeah, and on that point, Enzo, around this ability to kind of swap in another back-end solution, we ultimately ended up using a scalability solution that we came up with internally called BigMap. I'm wondering if you can share a little bit about BigMap and how it works. And we'll obviously dig into the details later today in the technical demo of CanCan, but maybe you could share a little bit about how that solution is a little different from your DHT solution.
BigMap actually is an implementation of a distributed hash table. It is a lot of the same ideas there. I think that there are some simplifications that were made to the code that things that we got for free from the platform. For example, typically with a lot of DHTs, you can set a replication factor to be, like 2 or 3, depending on how many times you want to maintain copies of a given file. Like in the case of DFINITY, you get replication failover for free, so we only need to maintain 1 copy. Like, that's a simplification. And other similar types of things where, really, I guess, where would I add context there too? Like in networking, for example. In DFINITY, there are no network interfaces associated with canisters. Canisters have canister interfaces, and the ability to call one canister from another is something that you get is a feature that's provided to you from the system. So, for example, you don't need to you don't need to think about replication. You don't need to think about networking, and actually for an implementation of a DHT in like some other more traditional context, dealing with all that stuff is like, it amounts to a lot of code, right? So for the end developer, it's less code that you have to maintain. So I wouldn't say it's very different per se, but I would say that you get a lot of simplifications and you get a lot of that for free, given the very specific properties that are provided by the platform. Maybe actually on the topic of scalability, I'd actually really like to maybe hear a little bit more from Rick, who's working on a current application right now in which you're actually, as I understand it, storing images of these watches. Is that right? And how you're able to actually kind of deal with some of the scalability aspects there. Have you tried plugging into something like Motoko BigMap or some of the other DHT implementations out there, be them in Motoko based or Rust based?
Yeah, so we're definitely going down that route of trying to figure out how do we actually store the models within DFINITY, and the BigMap is going to be one of the different ways that we're able to do this. We have thousands and thousands of images associated with the content that we're going to be putting on top of DFINITY, along with trained models that have been trained offline. But we're going to try to figure out, how do we put this trained model within inside of DFINITY and possibly use Rust to do the lookups against these models, if we can store those algorithms within inside of DFINITY itself.
So until everything is built on the internet computer, which is what we all hope for, there's probably going to be some need to build integrations and connections into existing systems that are kind of external to the internet computer. And David, you have a really cool example that I was hoping you could walk us through today around the ICP mailer that you've built. Can you talk a little bit about sort of what it was like to build those integrations into an existing system?
Yeah, so basically right now we have a gap between the internet computer and the traditional web. Basically, I have an example. How can I send an email from a canister, or how can I fetch some data from an API? Like I want to fetch the delivery status of a package on DHL. How can I do that from the internet computer? So as these services don't exist in DFINITY, we built a platform that fills this gap. So it connects the internet computer to some legacy systems. Basically, we created a proof of concept that allow Motoko developers to send custom messages to a 5.4Q canister. These messages are pushed to some legacy systems that we've built and via some external workers. So this platform is extensible. It allows you to trigger some calls back to DFINITY. The three main steps for the development of this platform were to develop this generic queue in Motoko. I imported using Vessel, a package manager for Motoko that I advise you to check out. And basically this queue has some restriction. Only some different canister ID or public keys can add some tasks, so there is some sort of authentication. The second step was to develop a web interface. So the second step was to develop a web interface that will deploy one queue canister per application. And finally, I think we developed a backend worker that will periodically fetch this queue canister and then process each message of this queue.
So Rick, you have experience along with David in building enterprise POCs in the decentralized space. And I know something we've talked about recently is how quickly you're able to kind of spin up prototypes and platforms for enterprise solutions. I'm wondering if you can just talk about just that process and sort of the time that's been cut down in the overall development process and getting some of these solutions in front of clients quicker.
Yeah, so we have a background in pretty much building proof of concepts inside of the decentralized space. And there's all these different types of layers that you always have to put together to make sure this is a successful project. Typically, you have some sort of front end communicating to a deployed back end. And when we built things with previous decentralized technology, at times it could have been a pretty heavy lift. You've got to host the protocol, then you have to have some sort of file storage, and you got to put it on a server. And then most likely you had some sort of man in the middle, some sort of database that was actually housing the data and maybe even a relay that would communicate to the decentralized technology, some sort of service bus in the middle. And building on a lot of what we've been talking about, all these things are kind of out of the box with DFINITY. DFINITY is the business layer. All the business logic sits inside with it, and it has the data layer. So all your data is stored and persisted inside of DFINITY, making the actual process of building the POC extremely easy. We basically need for these POCs is to store information, right? We need to be able to store, retrieve, and perform some sort of business logic. So all that exists inside of DFINITY, and it's just designing these modules inside of Motoko itself and testing them and creating your unit test and throwing it inside of the canister and then building your front end on top of it. And what is nice about the way that the DFINITY project is set up is right now, if we want some sort of front end, we want a traditional 3-tier architecture application, you just generate the project and you've already gotten like 20 or 30% of it done. It's all about designing the data types and creating the interfaces, typically some sort of simple CRUD stuff for a POC, and then building out that front end. And so it's super fast. It's pretty easy once you get over the hump of learning the language. But once you've put everything up and it's up and running, it's very easy to see it.
Great. Well, to finish us off today, I would love to do a bit of a speed round with you all. Some of the developers and folks joining us today may not have experience with building for the internet computer or the Motoko language. And I know at some point you were all new developers to the internet computer as well. So I'd love to just go around and share a few thoughts with the developers out there on how you got started and some of the tips that you would pass along.
I'll take that first because, gosh, there are so many resources out there for newbies. One of the best resources for me personally has been the forum.definity.org. There's a pretty active community of developers, people going. I think a lot of the content there is very much Motoko focused, but also people developing applications in other languages that are compiling down to WebAssembly. There's that. There are also the GitHubs of a lot of the core devs. A lot of them have got projects in Motoko and other and the likes that compiling down to WebAssembly and deploying to the IC platform. I personally have, I think, at least over a dozen projects, and some of these are pretty, and they range in complexity too, from something simple like implementing SHA-256 in Motoko to implementing a QR code generator to implementing a distributed hash table. There's a lot of examples there, and certainly for a lot of my colleagues as well. In addition to that, I would also say that there has also been content produced in the form of blog posts, and I wrote a blog post about this QR code generator in Motoko. So this was my first microservice on DFINITY. Actually, it's like a very self-contained microservice. I was like, I just want to deploy a microservice where I give it a string and then it sends me back QR code. Like, that's it. Well, it's the simplest thing I could do. So yeah, I wrote a blog post about that. Then also, there are these more complex applications that maybe aren't good for just starting out, but if you sort of evolve what you're working on and start doing something slightly more complex, there are apps out there like Linked Up and CanCan, sort of these open internet services that people are working on these days. And I think you can sort of start with some of those small pieces and then see how they fit together. And you go from maybe a very simple example, which is, I don't know, maybe like deploying a counter or your Hello World, to doing something much more involved and elaborate that has a user interface where you've got a much larger backend split across multiple canisters. Maybe you're streaming video data, pulling in images, and really actually just see just how little code you actually really need to maintain as an end developer in order to get something really cool off the ground.
That's great, Enzo. Thanks so much. Rick, David, any thoughts to share?
Definitely all of what Enzo is saying those are great resources. The DFINITY forums are amazing. The community there are very responsive. They're very helpful. Everyone's very straightforward with how they're going to help, and they're willing to dig into the problem with you, which I find very helpful. All the core devs, yes, even Enzo, going through Enzo's repositories have helped us quite a bit get through some basic problems of how do we even create these objects or data structures or functions. And actually the standard library itself is another big resource. I feel like most of the problems we wanted to solve, or we wanted to figure out how it was done, the standard library had some form of high-level answer for us that we could actually dig through and actually an answer.
So basically, I read all the example on GitHub. The Linked Up project was the first one that I looked at. After that, there is the content from Hans. He's doing like a podcast or a video, which is named Hack on the Internet Computer. It's on YouTube. And the forums were really useful.
So one last round robin before we close things out for the day. I would love to hear from each of you. What would you love to see built on the Internet Computer?
A Shopify built on top of DFINITY would be very interesting. The ability for anybody to kind of go in there and list some sort of goods for sale, even if it's digital or tangible or whatever, and build a little website around their store, and then have all the bells and whistles that DFINITY offers, as well as like other people being able to develop widgets or utilities for the Shopify application. I think it'd be very interesting.
May I get an idea around maybe a decentralized hubber on DFINITY? So usually, like right now, we have like a big companies that get all the fees, and maybe if there is something like hubber on that is open, could be really interesting.
Well, it's funny that you asked that question because I just got out of a hackathon actually that lasted for 2 days. So this was mostly people working in Motoko, but other languages that compiled down to WebAssembly and deployed on the platform too. I believe it was 12 or 13 teams. Working on some really cool stuff. That includes something like an open Zoom, which allowed people to do sort of this type of conferencing with with video communication. There was another app called Bookworm, which was kind of like an open publishing company. And then what was the other one? An application called Shield, which allowed people to link up with other people in their community to sort of get some help with this whole coronavirus thing that's going on. So getting your groceries, filling prescriptions and the likes. And yeah, so it's interesting. A lot of different people, a lot of different ideas, ranging in complexity from being very simple to much more involved. But that's really one of the cool things about the IC platform is that it's not like the sort of more traditional smart contracts that I think a lot of people who were in this space before were accustomed to using. You really can build more full scale style applications that can service hundreds of thousands of users.
Well, I'm really excited hearing about all of these awesome ideas. And the great news is that apps like Linked Up and CanCan, which have been very helpful for Enzo, David, and Rick in getting started, will all be open source, as well as many of the hackathon projects that Enzo just talked about as well. So we're hoping that kind of all the content that we talked about today in the panel, as well as these examples, will inspire you and get you started on your journey as you build on the internet computer. So thanks so much, everyone, for joining us. A special thank you to Enzo, David, and Rick for your time today, for sharing your valuable insights. And I know I'm excited, and hopefully the rest of folks are excited to get building on the internet computer. So thanks again.
As the Internet Computer project progresses towards launch, we're going to be releasing in-depth technical materials. But let's start off today with a very high-level view of how the system works. As previously mentioned, the ICP protocol is a blockchain computer protocol. One of the things that makes the protocol unique is that it has an open onboard governance system called the network nervous system. The network nervous system is responsible for controlling, configuring, and managing the network. The Internet Computer Network is constructed from a hierarchy of building blocks. At the bottom, you've got data centers. And you might imagine that in 10 years, there are thousands of data centers in the Internet Computer Network. They host standardized node hardware. And in 10 years, there'll probably be millions of these node machines in the overall network. These node machines are combined to create something called subnets. And you can imagine there might be hundreds of thousands or millions of these subnets. Subnets host canisters, which are the interoperable compute units that are uploaded by users. And there might be billions of these within the network. The network nervous system is responsible, in a sense, for managing the data centers. Data centers get into the network through applying to the network nervous system. So the network nervous system is responsible for inducting data centers. In that sense, while the network nervous system itself is an open governance system, it permissions participation in the network. In a sense, it plays a role equivalent to ICANN on the internet, which, for example, doles out autonomous system numbers for those that want to run BGP routers. The network nervous system actually plays a wide range of network management roles. For example, it monitors the node machines looking for statistical deviation that could indicate underperformance or faulty behavior. The network nervous system also plays a key role in the token economics of the network. Token economics is a broad subject on the internet computer. The network nervous system generates new ICP tokens to reward nodes that are being run by data centers and neurons that are voting within the network nervous system, which is how it decides on proposals that are submitted to it. When the network nervous system creates new ICP tokens to reward data centers and neurons, it's inflationary. If you're wondering, ICP tokens used to be called DFN. Eventually, data center owners and neuron owners take their tokens and exchange them with canister owners and managers. Canister owners and managers take these tokens and convert them into cycles and use those cycles to charge up their canisters. When those canisters perform computations or store memory, for example, they burn their way through the cycles, and eventually they have to be recharged with more cycles to continue running. That's deflationary. To understand the internet computer, you have to understand the concept of subnets, which are the fundamental building block of the overall network. A subnet is responsible for hosting a distinct subset of the software canisters hosted by the overall internet computer network. The network nervous system combines nodes from independent data centers when constructing subnets. This enables ICP protocol math to ensure subnets are tamper-proof and unstoppable using Byzantine fault-tolerant technology and cryptography developed at DFINITY. Although subnets are the fundamental building block of the overall internet computer network, they're transparent to users and software. Users and canister software only need to know the identity of a canister to call the functions that it shares. This transparency is an extension of the internet's fundamental design principles. On the internet, if I want to connect to some software, I only need to know the IP address of the machine the software is running on and the port that the software is listening on. On the internet computer, if I wish to call a function, I only need to know the identity of the canister and the function signature. In the same way the internet creates seamless connectivity, we have created a seamless universe for software, where any software, given permission, can call any other software directly without knowing anything about the underlying workings of the network. The internet computer also ensures the transparency of subnets in other ways. The network nervous system can split and merge subnets in order to balance load across the overall network. This is also transparent to the hosted canisters. In this example, we've got an imaginary subnet, ABC, which hosts 11 canisters. The network nervous system tells it to split. Subnet ABC continues with canisters 1 through 6, and a new subnet is spawned, XYZ, that continues with canisters 7 through 11. None of the canisters involved will have experienced an interruption in service. When you upload your canisters to the internet computer, you have to target a specific subnet type. There's actually a special subnet that hosts the network nervous system, but you can't upload your canisters to that. Instead, you have to target a subnet type such as data, system, or fiduciary. The subnet type grants your canister certain properties and capabilities. For example, if your canister is hosted on a data subnet, it can process calls, but it can't make calls to other canisters. For that, you'll need a system subnet. If you want your canister to be able to hold balances of ICP tokens or to send cycles to other canisters, you'll need a fiduciary subnet. And for those kinds of reasons, governance canisters can only be hosted on fiduciary subnets too. The capabilities of subnets partly derives from the underlying fault tolerance. This is a really exciting area of the underlying science that I hope to explore in future talks. For example, we've got new cryptography that allows the network nervous system to repair broken subnets. Of course, the purpose of subnets is to host canisters, so let's take a look at how they work too. Canisters run within dedicated hypervisors and interact with each other via a publicly specified API. Inside a canister is WebAssembly bytecode that can run on a WebAssembly virtual machine and the pages of memory that it runs within. Typically, that WebAssembly bytecode will have been created by compiling down a programming language such as Rust or Motoko. that will have incorporated a runtime that makes it easy for the developer to interact with the API. On the Internet computer, the functions shared by canisters must be invoked in one of two ways. They can either be invoked as an update call or a query call. The essential difference is that when you invoke a function as an update call, any changes that it makes to data in the canister's memory are persisted, whereas if a function is invoked as a query call, any changes that it makes to memory are discarded after it's run. Update calls make persistent changes, and they're also tamper-proof. They're tamper-proof because the ICP blockchain computer protocols run them on every node in the subnet. As you would expect, the calls run within a consistent global ordering of calls, using mechanisms that allow for concurrent execution within a fully deterministic execution environment. Update calls complete in just 2 seconds. In this example, a user submits a buy order to a financial exchange hosted within a canister. Query calls, on the other hand, don't persist changes. Any changes they make to memory are discarded after they run. They are very performant and inexpensive, and complete in just a few milliseconds. This is because they don't run on all the nodes in the subnet, which also means they provide a lower level of security. In this example, the user is asking for a custom newsfeed and gets back freshly generated content almost immediately, providing a great user experience. One of the coolest things about the Internet computer is the way that developers persist data. Developers don't think about persistence. They just write their code and persistence happens automatically. It's called orthogonal persistence. That's because the Internet computer persists the memory pages in which code runs. You might be wondering how all this works. With respect to update calls that can mutate memory pages, canisters are software actors. That means there can only be a single thread of execution inside a canister at any one time. However, by default, update calls can be interleaved. That occurs when update calls make cross-canister update calls which block. This allows the thread of execution to be moved to a new update call. Query calls, by contrast, don't make persistent changes to memory, and this allows there to be any number of concurrent threads processing query calls inside of a canister at any one time. These query calls run against the snapshot of memory recorded in the last finalized state root. Finally, no discussion of canisters would be complete without mentioning that canisters can create new canisters and that canisters can fork themselves. You can create a new canister simply by specifying the WebAssembly bytecode, and the memory pages start out empty. When a canister forks itself, a newly spawned copy is created that's identical down to the memory pages inside. Forking proves very powerful when creating scalable internet services. Let's finish up by talking at a high level about internet services that scale out. Canisters have upper bounds on their various types of capacity. For example, a canister can only store 4 gig of memory pages. For this reason, when we want to create internet services that scale out to billions of users, we have to use multi-canister architectures. We might hope that it's enough to create some special canister, create lots of copies of the canister, and then shard user content to the different canisters in order to create an internet service that can scale out. Unfortunately, this architecture is too simple for a number of reasons. It is true that each additional canister increases the overall memory capacity. It's also true that each additional canister increases the overall update and query call throughput. However, we cannot scale query call requests for a specific user's content. For example, maybe one of the canisters holds Kim Kardashian's data, and there's an awful lot of that needs to be served. We also need to rebalance user content whenever we increase the capacity of the system by adding more canister shards. And it's not really a great edge architecture, and there's no obvious way to serve query calls to end users from replicas that are in close proximity to them. We're actually going to need both front-end canisters and back-end canisters. The Internet Computer provides some really cool features for connecting end users to front-end canisters. One of these allows domain names to be mapped to multiple front-end canisters via the network nervous system. When an end user wishes to resolve such a domain name, the Internet Computer looks at the totality of replica nodes in all the subnets hosting the front-end canisters and returns the IP addresses of the replica nodes in closest proximity. This results in the end user executing query calls on nearby replicas, reducing the inherent network latency and improving the user experience, providing the benefits of edge computing without a content distribution network. To make the best use of this functionality, we need a classic architecture involving front-end canisters and back-end data bucket canisters. In this example, a web browser wishes to load my profile picture. First of all, the web browser will be mapped to a front-end canister that is running on a subnetwork with a nearby node. The web browser will then submit a query call request to retrieve the photograph to that nearby node. Front-end canister will then make a cross-canister query call request to the data bucket canister that holds the photograph. Of course, the data buckets will be managed using a standard library class such as BigMap. It's very easy for the developer. If the query call response returned by the data bucket canister involves static content such as a photograph, then it can mark it as cacheable. In such cases, the replica node that's running the front-end canister's query call can enter the query call response into its query cache. Of course, the query call caching mechanism is completely transparent to the front-end canister code. Once the front-end canister that the user called has collected all necessary information, it can return the content either through a query call response or through an HTTP endpoint. Over time, the query caches of nodes accumulate static content and generated data that is of interest to nearby users, providing them with a faster, better user experience. In this way, the native edge architecture of the Internet Computer provides the benefits of a content distribution network, but without developers having to do anything special and without the need to enlist the help of a separate proprietary service. For update calls, the classic architecture takes a different approach. It's necessary to serialize updates to a user's content and data to prevent problems like lost updates. Typically, this is achieved by mapping a user to a specific front-end canister just by hashing their username, for example. Once a user experience running in a web browser or on a smartphone, say, has determined which front-end canister is responsible for coordinating changes to some content or data, it can modify that content or data by submitting an update call to its standard interface. This front-end canister then typically makes more cross-canister update calls to effect the changes needed. Okay, to wrap this all up, let's think about designing an open internet service using our two-level architecture with front-end canisters and back-end data bucket canisters. First of all, when you write your front-end canister code, you're going to make your life easy by using an existing library class called BigMap. BigMap can store exabytes of data, and you can write objects to it using just one line of code. This architecture will transparently and dynamically scale out by having front-end canisters and data bucket canisters fork to divide responsibility for objects assigned to one canister between two canisters. Finally, to create a true open internet service, you'll assign responsibility for all your canisters to an open, tokenized governance canister. If you're an entrepreneur, you will raise funds for development by selling some of those governance tokens in the early days. And you'll probably design schemes that incentivize early participants in your internet service by giving them governance tokens to get better network effects and win. Thank you.
Thanks so much to our wonderful guests and moderators for such a lively discussion. During the conversation titled Billions of Dollars Waiting to Invest in the Open Web, it was exciting to hear about how there's continual investor appetite for developers building projects as part of the growing ecosystem of the open web. It was also great to hear about the experience of building on the Internet Computer from our guest, Rick Porter and David Fawn from the Origin Project, and DFINITY engineer Enzo Haussecker.
Next up, we have some really exciting demos for you. First, we have DFINITY senior researcher and engineer Joachim Breitner walking us through how to build with Motoko, the programming language optimized for the Internet Computer. Next, DFINITY senior engineer Hans Larsen will demo Rust on the Internet Computer. This proves that developers can use any language that compiles to WebAssembly to build applications. And last but not least, DFINITY engineering manager Stanley Jones will walk us through CanCan, a decentralized scalable video sharing app running on Tungsten.
And to introduce the demos, we have Andreas Rosberg, co-creator of WebAssembly and DFINITY principal engineer and researcher, to kick things off and give a little bit more color around building on the Internet Computer.
Welcome to the second demo section of this event. I'm Andreas Rosberg. I'm the technical lead of the languages team at DFINITY. I also happen to be one of the co-designers of WebAssembly, so that's probably where I want to start off with a few words on that in my little presentation here. So WebAssembly, in case you're not familiar with it, is a portable, hardware-independent representation for machine code. It was originally developed for the web, but it was intentionally designed with a much broader range of applications in mind and has been since adopted in quite a few other domains, which I don't want to go into here. Some of its features, like its meta-level features, are that it has like a fully deterministic and a fully sandbox execution model. It also has a specification that is mathematically formalized and has been machine verified for correctness and soundness. So it provides a very high level of assurance, which is like a perfect match for the Internet Computer and the kinds of apps we envision running on it in the future. At the same time, it provides almost all the expressiveness of actual hardware. And with this release, we take advantage of that. With this release of Motoko, we take advantage of that in one additional sense, that we are kind of like the first blockchain-based platform that can actually support floating point types and operations in our language. That's just one example of how that benefits us. Dom already introduced you to the basic concepts of the Internet Computer. So an app materializes as a canister, as a so-called canister on the Internet Computer. And a canister now is simply represented as a WebAssembly module, a module of a certain shape that you upload to the Internet Computer. Where this module is instantiated, meaning that it's brought to life along with the state, the memory state it encapsulates. And this state will persist on the IC, on the Internet Computer. So for an application, there's no need to explicitly save any data between invocations. And once you have installed a canister, like you can have a web front end that calls into it through some HTTP endpoints. At the same time, canisters can also communicate with each other, so there can be communication among different canisters through an asynchronous messaging mechanism, and I'm gonna get back to that a little bit later. So one of the advantages of using WebAssembly is that in principle, any language can compile to WebAssembly. So our vision really is that you can program the Internet Computer in any language of your liking. And to support that vision further, we have also defined a language agnostic interface definition language that we named Candid, and that allows applications, so canisters, to specify their interface such that canisters developed in completely different or unrelated languages can communicate with each other in a seamless manner. Having said that, WebAssembly is still a rather young technology, so there are only very few mature language implementations available at this point. One of them is Rust, so we provide support for building canisters and apps on the internet computer in Rust out of the box. But Rust is a very low-level language, so from our point of view, it's not ideal for most of the use cases that we have in mind for the internet computer. And that's why, despite all the risks of creating yet another programming language, we designed Motoko, which is our own brand of a programming language, and whose the intention there is to showcase our vision of what a nice programming environment for the internet computer would look like. And for that, we wanted a language that looks familiar and is easy to use to like programmers that are familiar with mainstream programming technologies. But at the same time, we also wanted to be safe and help avoiding unnecessary bugs in programs. But most importantly, the primary goal is to have it expose the concepts that the internet computer platform has in the most seamless manner. So concepts like canisters, asynchronous messaging, persistence, upgrading of canisters, but also in the future, things like token economics, which are not there yet, but will have to be eventually. So in order to meet these design goals, in order to look familiar to programmers, we chose to make Motoko look like a lot like Java or JavaScript languages you're familiar with. So with curly braces, semicolons, and all that stuff you probably have seen a lot. But this is really just a superficial skin in a way. Under the hood, we try to take in many of the lessons that have been learned in more than 6 decades of history of programming languages and research on them, and try to avoid many of the popular mistakes you tend to see in mainstream languages. So Motoko incorporates many features of modern programming languages, like flexible and a provably sound type system, freedom from problems like null pointer exceptions, so Tony Hoare's famous $1 billion mistake. Number types have built-in overflow protection. We have closures, we have rich variant types with pattern matching, where the compiler would tell you if you forgot to cover some cases, like in a switch statement. And the design generally errs on the side of safety and minimizing footguns for the programmer. But the most visible feature of Motoko is its built-in support for canisters and messaging in terms of syntactic constructs directly available to the programmer. So in Motoko, canisters are expressed as actors. So a canister really is an actor. If you're not familiar with that notion, an actor is a pretty old idea, 40 years old actually. It's more or less like an object. So an actor understands a set of messages, it encapsulates some state. But the difference is that messages are always asynchronous, so you can only send them one way and you don't get back a direct reply. They don't have a result. You can only send back messages the other way. And they're also always atomic, so every actor receives messages in an atomic sequential fashion. And that makes actors a great model for concurrency and distribution. In particular because it automatically prevents a whole class of concurrency bugs that you often find in software, like race conditions cannot happen because everything is atomic and state is encapsulated. And also deadlocks cannot happen because execution never actually blocks. You can only send out messages and then you receive new messages. You don't have to wait for a reply before you can receive the next message. And as I said, that avoids many of the classical concurrency bugs without the programmer ever needing to define any lock or similar mechanisms. And that's what actors actually have originally been invented for. And the other important aspect of the Motoko programming model is that it has direct support for persistence, sometimes called orthogonal persistence, meaning that it's sort of transparent to the program that its state just persists across execution. So on the internet computer will just persist an actor's, aka a canister state, between invocations. So this gives a program implemented as a canister the illusion of running forever. And this is pretty great, but of course the devil is in the details here, and this is an approach that has often failed in the past, because there's the tricky question of how to deal with software upgrades, right? So you have a running application, but now you need to fix a bug or extend the functionality. You actually need to load new code. And in the latest version of Motoko that we're releasing now, we're supporting that through a notion we call stable variables. So in a Motoko program, the programmer can declare a certain set of variables in an actor as stable. And thereby they commit to these variables not changing their types in incompatible ways in the future. So when the programmer writes a new version of that canister, it still has to use these variables. They can add new ones, but the existing ones they cannot change in an incompatible way. And because of that, the upgraded canister can then safely inherit the old value that the stable variable has from the old version of the software. And the runtime system and the language implementation at the same time ensures that the representation remains compatible, even across different versions of a compiler, for example. Yes, so with all that in mind, I want to introduce you to the 3 demos you're going to see in this section. And these 3 demos are supposed to showcase some of these ideas I just told you about. So the first demo is going to be by Joachim Breitner. He will show you how to program a canister in Motoko, with a particular focus on how to upgrade a canister with a new version with existing functionality using stable variables. And after that, Hans Larsen will show you how to write a canister in Rust using his autonomous chess application. And finally, Stanley Jones will give you more technical background about the CanCan demo, the simple video sharing app that you already saw a teaser for earlier. So enjoy!
Hello, I'm Joachim Breitner, one of the researchers and engineers on the Motoko team, and it's going to be a joy to present to you the Motoko programming language, one of the languages that you can use to create services on the Internet computer. And in the following live coding demo, I will not only show you what it means to program Motoko, but also what it means to program Motoko on the Internet computer. So we will be creating a small toy service, and we will see how we can evolve the interface of such a service without breaking any of the existing running clients that are written in possibly other languages, other environments. And we will also see how you can swap out the functionality and code of a running service without losing the state of the running program. So without much further ado, let's get started. I'm going to write a little service that is a mathematical expression evaluator, like a little calculator. So for that, I'm going to write a type for a mathematical expression. And this is either a constant of type int, or it's an addition of 2 expressions, or it's a multiplication of 2 expressions. And this is a variant type, which is similar to what you might know as sum types or enums in Rust or other languages. And then I can write a function called eval, which takes such an expression and then returns the integer that it evaluates to. And there I can use the switch statement to analyze the expression and look at the possible cases. So it could be a constant, in which case we just return that. It could be an addition, in which case we call evaluate recursively on the sub-expressions and then add the results. Or it could be a multiplication, where we do the same and then we multiply. Now I've just written this functionality, now I want to expose it to the public as a method of my service that people can use. And for that, I need to define a public function, which I'm going to call calculate. It also takes an expression and returns an int, but it returns the int as an asynchronous value. This is crucial because our platform has this notion of, it's built on the actor model, so all these services are talking to each other via asynchronous messaging, which means you get the response eventually later. And you can model this as an async type. It doesn't really affect how we write this function, so we can just say we return the valid. So my IDE here seems to be happy, so hopefully this program compiles. And once it's built, I can deploy my service as canisters onto a locally running version of the internet computer. And once it's running there, I can use it from, well, I can use it from whatever I want. The key here is that we've defined an interface description language called Candid, which allows cross-language interoperability. So we can look at the automatically generated Candid file here, and this says that this service provides a function called calculate with the following types, and it also includes a definition of the type. And now I can use the service, for example, from the command line, where we can see that 1 + 2 is 3. A bit more convenient than writing this rather tedious syntax for Candid values might be the Candid UI. So this is a great tool for rapid development, because without writing any code, just by giving the definition or by having this description of the interface, it automatically generates a UI for us. So here I can now add the multiplication of, let's say, 8 with 5, and then we add the constant 2, and we can see that this also now talks successfully to the service and returns the result. Another way of talking to the service might be from a browser using JavaScript. JavaScript is not so much my thing, so you will see more of that in the next demo by Hans. Instead, I'm going to use my service now from another service, because a crucial idea of the computer is that when you create a service, it's not only usable from the particular front-end UIs that you're building, but rather all the other services can use it, and you can mesh these services, and everything's nice and open and accessible. So let me switch to this file, where I want to use the calculator to, let's say, print out a sequence of square numbers. So here you can see that I'm importing the calculator canister, which means I have to do nothing, and it already knows, like the compiler and IDE, what service the calculator is, what its method names are, what the types are. This whole expression thing is now available to my code here. So in order to write this counter, I first need some state. So I have a little counter, and then I write a public function next, which returns, again, asynchronously an integer, and it bumps the counter, and then it calls on the calculator the calculate function, and it wants the multiplication of the constant n and the constant n. Now the IDE now tells me this is not quite right, because this is a remote call. What I do when I invoke this function is at first an async int. An asynchronous value is still a promise. And here I really want to wait for the result to come back. So I do that by using the keyword await. And now the compiler is happy. So let me build the canisters and then install the squares canister. And now I can call the next function, and we see that the first square number is 1, and subsequent ones happens to be 4, and then we should get 9. This is a bit slower than the previous call that I did, because now it's entering this internet computer, it's talking between these two services, going back and forth, and then returning the result to me. So it's slightly slower. All right, let's go back to our calculator, and imagine that our calculator service has gone through the roof. And we now have many, many clients, but we still want to evolve the system. We want to add new features. So let's say we want to add subtraction. So I can add it to the types. Then the compiler is telling me, wait, you also have to add it here. So this is nice. This avoids bugs that I have to make this pattern match complete. But what happened now is that I've changed the interface. If I now build this and deploy the new calculator, did I just break all the existing clients for my service? Well, no, because some changes to the interface are okay. And Candid has a built-in notion of what evolutions of the interface are safe. And if I would make a mistake here, then the tooling and the platform will prevent me from accidentally breaking the interface. In this case, the interface upgrade is fine. So I can still use this Candid UI, which I haven't reloaded. It's still the same code. It's like as if somebody was still using the app without having upgraded it. And also my lovely squares canister happens to continue to work just fine. So let's look at the square canister again. And notice that it has persistent state. So far I've always reinstalled these canisters, as I do now again for the squares canister. And reinstallation means wipe all the state, wipe all the code that you have, and just here's the new thing. And if you do this, then of course the squares canister begins counting again at 1. So let's say I want to change the square service without losing my state, because the state might be more valuable than just this counter. It might be my business data. Well, let's do a little change to the system. Let's say we want to make bigger steps here. So let's say we want to step in the thousands. Oh, you know what? Let's do the million. Well, I have to build it. In order to now deploy this bug fix or this change of feature without losing my data, I have to make sure that I install it with the upgrade mode. And this means the system will replace the code of the running program while preserving the state. And again, the tooling will make sure that if you do so, you don't change the, let's say, types of your state in a way that would lose your data or that would be incompatible. So let me upgrade the squares canister. And because I've used upgrade, if I now call next, we will see it has the new features, but it still has the old state. We didn't start at 0, as you can, I guess, see from the 4 and the 8. So that's all I wanted to show you in my Motoko demo. There's more that's new in Motoko for Tungsten. In particular, we have a more complete base library with documentation even that you can use to build more interesting things. And of course, there are plenty of other features of the internet computer that I couldn't show you now that are exposed through Motoko and are to be used easily. With that, thank you for your attention and enjoy the next demo by Hans about how you can write these canisters in Rust.
Hi, I'm Hans Larsen, engineering lead on the SDK team. What I'm going to show you is a fully working chess engine running on the internet computer. This is a very simple front end made in JavaScript that starts a new game, and the game happens on the internet computer itself. Every move I do triggers the engine to calculate the next move. You could imagine this being a game against another person on the internet, or multiple people voting for the next move against a chess master. Or this could be an entirely different game, like a card game, or even a lottery system. Since nobody owns the code or the game, nobody can mess with it. In this demo, we're going to show you how to build a chess engine running on the internet computer with Rust. So this is a good example of how you can use another language than Motoko to build canisters and run them on the internet computer as if they were native code. So first, like any cargo projects, we're going to create a new library called chess. And inside of it, we're going to open up in our favorite editor This is a standard Rust library. There's no magic here. This is entirely what you get when you create a new library in Rust. We're going to create a new DFX JSON, which is the configuration for the DFX CLI tool and we're going to create a new canister of type custom that actually run cargo build in order to create this the WASM, the WebAssembly output. And we're going to tell DFX where to find that WASM and what is the API of our canister. So the next step would be to create that API because it doesn't exist yet. And so we're going to create the API for our chess canister. And this API takes 3 methods, creating a new game and telling it whether we want to be the white player or the black player. And it's going to take a move, which takes the move in a UCI notation and returns whether it's a valid move or not. And we're going to have a way to get the state of the board, which is a query method. That means that it doesn't update the memory. Same in Motoko when you do query methods. Now let's add our dependencies. So because this is a Rust canister, we need to add the Internet Computer canister development kit for Rust to our project. And right now this is not public, but it will be for Tungsten. And the last dependency that we need to tell it is Pleco, which is a chess engine. And we're going to use version 0.5.0 for that. Next, we're going to remove the default tests, and we're going to add the method for creating a new game. So we import everything that the CDK has to give us. And we're going to import the board from Pleco. So the new method just creates a new board by calling the storage API that we published. This is simply a way for users to use storage. They can use globals or any kind of heap allocation. We just make it easy for users to create new objects that will be persistent between calls. You can see that I specify here that I want this to be an update method, and this will make it public under the name new. It takes a bool and return an optional string. And the optional string is the move that the AI will do. If I'm the white player, there's no move because I'm the one who's supposed to make the first move. But if I'm a black player, the AI will make the first move and will return it to us. So now that we created the new board, we need to have a way to make a move in it. So here I export a new function called UCI move, but I rename it to move. This is an update call, so it will change memory. And it gets the same board as created in new, and then it applies the UCI move, which is a function provided by Pleco. We don't even use that, so we just reuse existing code. And if the move is valid, we return true and the AI move. And if it's not valid yet, we just return false with no move because the AI will not play for you. Finally, we implement the AI move itself. We create a clone of the board, and then we apply a searcher on it, which is the AI itself, which is Stockfish. And we search for the next best move. We apply it to the board, and then we return its version stringify in UCI. And the last one is how to use to get the fen notation, which is we get the same board and we just return the string for the fen notation of the board itself. Now we're going to build this using DFX build, as you would for any projects using DFX. You just run DFX build, and it takes a minute or two, and it will give you the WASM and the DID, and it will create canisters for it. And then we can just install those. There is absolutely no difference to the workflow between Motoko and Rust once you've set up the configurations. You just use DFX build, DFX canister install, and DFX canister call like you would a generic Motoko workflow. Once this is compiled, we can just call canister install with our chess canister, and we will see that it installs correctly. I have a replica running in the background. And now I can do DFX canister call chess with new, and I'm going to say that I'm the white players for now. So since I'm the white player, it didn't return any move. So my first move should be e2 to e4. And we'll see that the computer returned true because this is a valid move. And it returns c7 to c6, which is the move that the computer did. And now if I do d2 to d3, the computer did d8 to b6, which is knight. And I'm just going to do a1 to a2, just to show a1 to a2. And this is not a valid move, so the computer just says, nope, you cannot do that, and nothing happened. The board stayed the same. Finally, I have the getfen method, which returned me the current state of the board in fen notation. So if you know how to read that, like, you would see how the board would be at this moment. And so as you can see, there's multiple points to this here. One, it took me less than 5 minutes to build a fully functional chess canister that people can use to play chess against an AI. Two, once we set up the configurations, using Rust is no different than using Motoko with DFX. Everything is made easier. The three, there is nothing preventing us from using Rust and building anything that can target WebAssembly to build canisters for the internet computer. Motoko is just one language that's specialized for the internet computer, but we can use Rust or we can use any other languages for this. Any other languages that build to WebAssembly. Everything that is local here can be also built for the internet computer, for the Tungsten network, and sent over there, and nobody can own it. So if you wish to create a canister that nobody owns and play chess against it, or play a lottery that nobody can tamper with, this is definitely easy to make and would take you a few minutes. You can also see that to communicate with the Rust canister, we use Candid, the same we would use for Motoko. So there is absolutely no difference for the client side whether the backend, the canister is coded in Motoko or Rust. Everything uses Candid to communicate with it, and it integrates seamlessly with other canisters as well, which know and understands and uses Candid. So you could have a canister that just calls this chess canister from Motoko or from another language that builds to WebAssembly, and have those play chess against each other. But we can use Rust or we can use any other languages for this. Thank you.
Hi, it's Stanley again. I've been watching some silly dancing cat videos streaming straight from the internet computer on the latest example app from DFINITY developer experience team. We call it CanCan. let's take a deeper look at how it works. So last fall, we launched the Motoko programming language and our SDK. And at the time, I showed you a very simple to-do app. It ran in the terminal on my laptop. And then this spring, we launched a test network. So I showed you a desktop web app that ran in a single data center. CanCan is a mobile video sharing app distributed across multiple data centers. So 6 months ago, we were showing you the 1970s era computing, and now we're already up to the 2010s, which puts us on pace to hit the year 2050 by this winter. Our last app, Linked Up, was composed of multiple stateful modules, or canisters. And one served the front-end assets and the API. The other handled social graph behavior. There was no database because all of the data was persisted by declaring standard data structures like arrays, maps, trees. For CanCan, we again have multiple canisters working together. This time, the first canister is only serving the front-end assets, which we've written in TypeScript using the React framework. But you could use Vue or Angular or even no framework at all. Connecting to other canisters is even simpler than a standard XHR. You import the canister by its alias, which the SDK can resolve at build time, and then you can call any of the public methods of your canister in your code. The second canister is holding all of our data. It's sort of a distributed hash table that we've implemented in Motoko. And not just the metadata and content hashes are stored here, but the video bytes themselves. And then we are sliced into chunks and stored to be retrieved, reconstituted, and then played as a video in the front end. So we can request a video, and the back end will either respond with data or it will request the data from one of its peers. And that ability to shard and rebalance means that my storage scales as needed, so I'll never run out of space. Now, Dominic challenged us to build a library like this one, which we call BigMap, so that developers could write a scalable app in less than 1,000 lines of code. Actually, he said 500 lines of code, but we talked him up to 1,000. For CanCan, we did it in 0. There's no other backend than this library. BigMap has a simple interface, put and get, and that's all we ended up needing in the front end. The scaling happens painlessly and out of sight. In fact, if you kept the same interface, you could swap the implementation for a canister written in an entirely different language, which is what we did. The Rust implementation takes advantage of non-mutating queries, which are blazing fast on the internet computer. So we make one lookup to an index canister and then another query to a data canister with the canister that the first result responds with. Now these queries resolve in milliseconds, so our first byte of data arrives in less than a second. Every service running on the internet computer is completely interoperable with every other, regardless of the language in which they were authored. So once your code has been compiled to a WebAssembly module and then installed as a tamper-proof canister, services can be seamlessly composed as easily as importing a library. Speaking of installing, I actually noticed a typo in our app earlier. So let's quickly fix it and update our canister. CanCan here should clearly be lowercase. If I make the change and rebuild the app, you'll see I get a few warnings because I'm using an unreleased version of the SDK. Now when I deploy, I can specify whether I want to reinstall with a fresh state or upgrade only the code while keeping the state intact. And now if I take a look at my phone, you can see that the change is live and in the hands of my users in just seconds. So I deployed changes across a decentralized network running in data centers all across the world, about as fast as I could tweet that DFINITY is hiring SDK engineers. Let's recap. Streaming video on mobile device, written in multiple languages with painless scaling, updated in seconds. This goes beyond legacy software development, beyond smart contracts. This is app development in 2020. The network is live, applications are open, and I hope to see you soon. You'll excuse me, I need to go shoot some can-cans.
Thanks to Andreas Rosberg for your opening remarks, and to Joachim Breitner, Hans Larsen, and Stanley Jones for those wonderful demos.
Now that we've seen what the internet computer is capable of, we will be hearing from several industry experts on the future of computing and the internet. First, we're excited to introduce esteemed professor of cryptography Dan Boneh from Stanford University, who will walk us through generational shifts in computing. Next up, we'll have a fireside chat with none other than Chris Dixon from Andreessen Horowitz and Dominic Williams on rebooting the internet. Then we'll have a live AMA with Dominic Williams, moderated by our own Michael Hunte. Please be sure to submit your questions that you'd like answered by entering them into the chat.
Thanks, Alexa. Everybody, without further ado, please give a warm welcome to Professor Dan Bonnet from Stanford University, who will be walking us through some of the most momentous generational shifts in technology.
So computing has come a long way, from mainframes and dumb terminals back in the 1960s, to workstations and local computing in the 1980s, to network systems in the 1990s, and then back to centralized cloud computing in the 21st century. Right now we're at the beginning of the next cycle, where decentralized architectures are being built. So to see why, let's think back to the local computing era, where applications that I bought and installed on my machine ran locally on my system. All my data would live on my system, and the application would always run on my local machine. If it ran today, it would run tomorrow, and would run a month from now. The interesting thing about the local computing era is that even if the developer went out of business and disappeared, I could still continue to run the application long after the developer is gone. In the old days, I had an editor that I liked to use, and I used it for many, many years after the developer had disappeared and stopped supporting the editor. So that was all possible because we ran our applications locally, we kept our data locally, we installed our programs locally, and we were kind of responsible for managing our local computing environments. With the shift to cloud computing, things have changed dramatically. First of all, our applications are now run by third parties, and that brings tremendous benefits to our computing environment. Data mobility is much easier. If I use my computer today and then a different computer tomorrow, it's much easier for me to move my data from one computer to another. Data sharing becomes much easier because everything is stored in the cloud, and sharing is just a matter of defining access control policies. And of course, the cloud does a pretty good job of protecting my data, much better than I could do locally, probably, in protecting my own systems. However, it's important to remember that these benefits come with a price. Yeah, so we no longer run our applications on our own systems, and all of our data lives in third-party servers. If an application developer decides to shut down an application that I like, I'm out of luck. Yeah, I'm powerless. I can no longer use the application. I might have gotten used to the particular workflow of that application, but if the developer decides to shut it down in the cloud, well, I have to find a new application to use and get used to the workflow of that application. Yeah, so the application simply stops working and I can no longer use it. What's interesting is even if I'm willing to pay to use the application, there is no one to pay. The application is simply no longer available and I just cannot use it. If I'm lucky, before the application developer shuts down the application, they'll tell me that they're doing that and I can extract my data from the cloud. But even that's not guaranteed, right? There are cases where a cloud application might get shut down and users will end up losing their data that they had in that application. So this is very different from local computing. We are now dependent on third parties to run the applications that we use, and we're depending on them to keep our data and keep it secure. So decentralized architectures offer many of the benefits of cloud computing, but can alleviate some of the risks. So first of all, even if an application developer disappears, the application will keep running. Second of all the resources that I have at the application will stay mine forever. And third of all, the decentralized nature of decentralized systems ensures an extremely high uptime so that I can rely on the servers and the application always being available. So let's drill into these 3 points for just a minute. So first of all, if an application developer disappears in a decentralized environment, the application is still running on the decentralized servers. If I wanted to interact with the application, I would simply send transaction fees with every transaction that I make, and the application would continue to process those transactions. My state and data would be updated, and I can keep working with the application as if nothing happened. It's quite interesting that in a decentralized environment, we don't need the original application developer to help run the application. The application simply runs on its own in the decentralized environment. What's even more surprising is that many decentralized applications are typically open source. And as a result, if the application developer goes out of business and disappears, it's very likely that an open source community will develop that will continue to support and update the application. So as a user, not only do I get the benefit of longevity, but also I'll most likely continue to get updates and maintenance just based on the open source community. Second of all, the resource that I have at the application are mine and will be mine forever. This is the beauty of blockchain-like systems where ownership is maintained by cryptographic keys. So as long as I own my cryptographic key, I'm the only one that can sign away resources that I have at the application, and no one can take them away from me otherwise. So think of, for example, a game or a financial application. In the context of a game, think of all the resources that I built at the game. Those resources all belong to me, and that ownership is maintained by a cryptographic key that I have, and no one can take those assets from me unless I properly sign away the assets and give them to somebody. Again, this is quite different from a typical cloud computing environment where the application developer is the one who controls who owns which assets, and if need be, can allocate assets differently. Third, because decentralized applications run on many potential servers, even if a large fraction of those servers become unavailable, the application keeps running as if nothing happened. As long as some servers are available to process requests, the application will continue to run. So decentralized applications, as a result, have an extremely high uptime, and I can rely on that being available to me and not have to worry about outages. So to summarize, decentralized architectures are actually much harder to build than centralized ones. Because of that, it's not surprising that centralized computing emerged first. But now decentralized applications are being quite heavily developed, and they might very well be the next step in the evolution of computing. Moreover, because of all the effort being put into developing decentralized environments, it is now much, much easier to develop decentralized applications, and developers, can take advantage of that. And we're very likely to see a huge explosion in the coming years in applications running in decentralized environments that, again, we can all interact with and get the benefits from. So maybe I have to say, I'm really excited about the space. I do a lot of my research in the decentralized world now, specifically with cryptographic applications to decentralized applications. I'm a cryptographer, so I find the crypto that's needed for decentralized applications really fascinating. We do a lot of our work now on developing crypto systems and crypto tools in support of decentralized applications. But even beyond the cryptography, basically decentralized applications are kind of a new programming paradigm. Yeah, when you write these applications, it's really quite different from writing applications that run on a standalone system. You have to think about how the different components of the systems interact with one another. There are different programming languages that are being used to write these applications. Even the runtime environments are actually quite different from what we used to in standalone computing. And so it's actually kind of a fun time to kind of get used to these new computing environments, new software systems, new languages that need to be used to develop these applications. So to capture all that, we actually are teaching a course on blockchain development and blockchain technology in general. We've been doing it now for the past 5 years. Students at the university are, obviously they're quite excited about all this development. The course normally has over 100 students enrolled, so there's quite a lot going on. We teach the students basically how to build these decentralized applications. When they're done with the course, they can actually go and build financial applications, gaming applications that take advantage of these systems. Generally, there are kind of what you need to know to build applications like this is know how to write the code that runs on the blockchain. Then you also need to know how to write the code that interacts with the blockchain and presents it to the users. And of course, then there's the user component, the user interface that interacts with those two mechanisms that are developed. And so to develop applications in a decentralized environment, you need to learn about new programming languages like Solidity, Motoko, and many others that are being developed. You need to understand how the environment actually operates. So there's typically these programs run inside of a virtual machine. You need to understand the costs of different virtual machine operations. Everything here actually costs a transaction fee. And so you want to minimize transaction fees for your users and even for you as a developer. And so there's a lot of knowledge that goes into how to write code for these environments that minimize transaction fees. There's actually also a lot of composability that's happening. So some developers are building software tools for decentralized environments that other software developers can take advantage of. So there's quite a lot of composability that we see happening. There are libraries being developed. There are services being developed that third parties can use. And so we're seeing sort of a growing ecosystem of applications where applications depend on one another for their operation, but all of them execute in a decentralized environment like a blockchain or an internet computer. And so there's a lot to learn. It's kind of fun to learn this new programming paradigm. I've enjoyed writing code for this environment myself. It turns out actually getting things to work correctly and securely is non-trivial, which is kind of what makes it interesting. And so there's also a lot of support that's being developed to help write correct code, secure code, code that doesn't have surprises that are going to come down the road. And so there's actually quite a lot of excitement and activity in the space. And the future is probably going to be even, we're going to see even more applications come out. And the ecosystem for these kind of applications is going to continue to expand. Personally, I'm really looking forward to playing with the development environment for the internet computer. I'm looking forward to downloading the development tools and using them to build sort of my own projects. In particular, I'd like to kind of use those projects in our blockchain class. So it'd be kind of nice. It'd be wonderful for the students to learn how to use this new development environment, the Motoko language, writing code that compiles into WebAssembly and runs on top of a WebAssembly-like system. And so I'm looking forward to seeing how the technology matures, and I'm hoping that the ecosystem will increase in size, and I'm excited for what's coming. I'm sure there's going to be a lot of developers who also want to get their hands on the tools and use them to build new and exciting applications. And I love the space. I think it's really exciting, and I'm really looking forward to what the next couple of years will bring.
Chris, good to have you here. Thanks for joining us for the Tungsten launch event. We've discussed platform risk many times before. And one of the big challenges of the modern internet ecosystem is that once tech companies reach a certain size, there's a tendency for them to stop innovating and restrict access to user data and relationships that they shared during their explosive growth phase, and then squeeze everyone in the mode of a monopoly. And this can be really harmful for the ecosystem. For example, there are a ton of startups incorporating professional profiles from LinkedIn into their own services, and then LinkedIn revoked everyone's API access. Can you give us some of your perspective on platform risk through the history of tech?
Yeah, so I think to start off, I'd say the core dynamic in technology, right, is you have platforms. So that could be something like an iPhone or an Android, or in the old days like Windows, or it could be a social network like Facebook or Twitter, or a browser like in the past Netscape, and today something like Chrome, and then applications built on top, right? So that's in the Windows era, that was Quicken and Microsoft's products like Word. In the social era, there were like Twitter clients, for example, like Tweety and TweetDeck, and Facebook had games like Zynga. The iPhone obviously has Uber and Instagram and all sorts of this rich app ecosystem. And so one of the reasons tech is so exciting is that you have this interplay between the applications and infrastructure, right? Someone like Apple invents an iPhone, then you have new applications, and those things create kind of a reinforcing feedback loop. And when those things really hit, if you look at the growth rates, they really like exponentially grow in their growth period. So like for the iPhone as an example, it was between 2008 and like 15, it just like explosively grew. And then if you look at the numbers, at some point it saturates, and that's what's known as the S curve, right? So it sort of goes it starts off, and it's called S curve because it starts off, it's sort of hitting product market fit, then boom, it hits, it shoots up. There's some period of, let's call it 5 to 10 years where it grows rapidly. Facebook, their growth period was like 2006 through 13-ish or something is when it really skyrocketed. And then, as you said, like at some point it kind of hits a saturation point. And I think we're seeing that, for example, the iPhone is the most obvious example today. We're just in the news last week, is the iOS store's practices. So Apple's iPhones have basically leveled out at roughly 1 billion devices. growing slightly, but not much. If you follow their kind of earnings reports, it's all about kind of services now, right? Which is their 30% take rate. And so they do a couple things. They have this huge kind of monopolistic position, and then they require all applications go through the App Store. You don't have a choice. And then they require, if you do go through the store, in many circumstances, you have to give them 30% of your revenue. Some big companies like Netflix and Amazon, if you notice, you can't buy Netflix or Amazon books in the on the Apple iPhone itself. You have to go to the browser or to a desktop. They sort of do that to get around things. There's just sort of cat and mouse game. Companies like Netflix and Amazon are big enough to really kind of fight off Apple. Startups aren't. And so this idea of sort of platform risk is this concept that if you're an entrepreneur or an investor in startups, is a huge existential risk that kind of looms over. It's this cloud that looms over all software development, essentially, is that at some point, if you're successful, the big guy that you're dependent on will come and kind of extract rents, right? It's and in worst case, in some cases, it's much worse. Like in the case of Zynga, Facebook just kind of changed all the rules that just kind of destroyed the economics. Twitter changed their API that just literally killed off overnight like a huge swath of startups, like Twitter clients and things that depend on an API. Microsoft very famously, went hard after they either tried to buy or build and put out of business all of their kind of main dependencies. There's books written about them taking on Quicken with Microsoft money and things. Famously Netscape and IE bundling that went to antitrust. So it's a huge issue, and I think really stifles. My view is it really stifles innovation. It stifles startups. When you don't have it. So for example, the web initially did. One of the beautiful things about the web is it was built on open protocol, so you didn't have that platform risk. The web wasn't going to change the rules on you if you built and YouTube or Facebook or Google. And of course, look what happened. You had this incredible period of innovation, right, where all these people, entrepreneurs, were willing to build these things, and investors invest in them, and decades of kind of investment went into them. And part of why all that investment went in, both in terms of time and money, was people knew that if you built something on the web, you could keep it, right? It's kind of like, one of the reasons the United States has been such a fertile economy is that, if you build something in the United States, you can, you have taxes and there's all sorts of things you have to do to give back to society, but in the end, you generally get to keep it. Whereas if you go to like an authoritarian country, where they, famously seize assets and things, you just see far less investment in those countries. It's sort of analogous to that. So it's a huge issue. One of the really exciting things with blockchains is that we're now, as we call it, kind of entering the Web3 era, where we think you can get the combination of kind of the advanced functionality of Web 2, all the richness and reasons why people love Twitter and Facebook and Gmail and all these other kind of modern applications, but the openness of Web 1, the lack of platform risk. Startups can really build on things. And obviously, that's kind of the kind of thing you're building at DFINITY, is that kind of infrastructure where you can build that advanced functionality and not make trade-offs, because the early web is limited in its functionality, but have the lack of platform risk that was associated with so much innovation in the first year of the web.
Yeah, I think there's an analogy there. The internet provided, it removed platform risk for connectivity. It provided a global public network to which anyone could connect services. And supply services without fear that their connection to the internet would be degraded or taken away from them by some centralized controlling party, because the internet is decentralized. But the internet only does this for connectivity. And the internet computer aims to extend that to compute, so that in addition to providing a open free market where people can connect services, we can also enable people to build services that others can build on, free of platform risk too.
To your point, there was a point in 2000, I would say 8 or so, having been there, I was an entrepreneur back then, when there were real competitors to proprietary social networks. So RSS and all the related protocols were essentially open alternatives where you could follow friends and follow blogs and do other things. But they really got obviously crushed by the proprietary versions. And a big part of it was you couldn't do certain things. Like, for example, you couldn't store, if I'm C. Dixon on Twitter, I can go to Twitter and sign up and be C. Dixon, and I can follow you on Twitter, and that's all just stored magically in the cloud from a user perspective. With RSS and things, you had to do all of these, you had to create a website and put this this markup language on your website that showed your friends list. There was no place on the web, there's DNS kind of, which is a limited storage thing, but web had no storage mechanism as an example, right? Which is, obviously in the system you're building, a key part of it is this kind of feeling you can just put stuff right in the cloud, my name and my friend list, and the internet computer will just figure out how to store it, right?
That's right. You can actually store data within the protocol, within the internet. So you don't need to put it on a proprietary platform like AWS or necessarily within a social network, say like Facebook. Somebody can build an open internet service into which users can put their data, and upon which other companies or enterprises or open internet services can build, because they're guaranteed access through the APIs that are provided, won't be revoked.
A question for you then would be, what if a cynical person says, how do I know there won't be change? How do I know DFINITY won't become evil? How do I know the application developer on top won't become evil? What protects me? How do I know this isn't the same thing over again that happened 10 years ago, the kind of bait and switch of the internet services that promised to be owned by users? Yeah.
That's a really good question. I think that, it boils down to the magic of blockchain technology, and having multiple parties running a platform via ultimately a consensus protocol that protects the users of the platform from the sort of faulty or malicious behavior of any individual participant. And ultimately the internet computer is designed in such a way that if somebody creates a permanent API, even if let's say, you have an open internet service, an open social network, say, that has a tokenized governance system. First of all, the platform won't allow you to remove an API that's been marked as permanent. But not only that, the framework has mechanisms that allow degradations of functionality behind an API to be reversed.
And it's baked into the logic of the system, as opposed to, and not everyone, of course, will be sophisticated enough to go and personally audit that system, but it's all open, and therefore anyone can go and audit it, and you can, as a user or a developer, know that you could always go in, read the code, look at the system, and have your guarantees promised by kind of math and software, as opposed to corporate commitments or legal commitments or other kinds of things we relied on in the past. I think it's what we're talking about. We're talking about from the developer perspective, is also the user perspective, right? Which is, the way I think about it is, I think one reason people are kind of unhappy with the state of social networking today is a couple of things, or marketplaces like Uber and other kinds of services like this. A couple of things. Like, one is they feel, or Airbnb, or just generally like kind of Web 2 products, is, I think one is some of the users feel like they helped build these services, and yet they didn't get to participate in the economics of them. Two, they feel like the platforms implicitly made commitments to them, like Twitter said, hey, this is an open place to tweet, and now suddenly they're kicking people off, changing the rules, changing the terms of service. So I would put those two into two buckets, right? Economics and governance. Another advantage of blockchains, in addition to making commitments to developers about APIs, permanence, things like that, like you're describing, it can also make commitments to users. So it can say to users, hey, you get some of the tokens for using this, or you can buy the tokens, or you can earn the tokens, and you get certain governance rights, and we can't change those. We're making those commitments to you in the code, and they're permanent commitments in the same way. So there's I think of it as a set of commitments to developers, which enables innovation, and then a set of commitments to users, which enables kind of good behavior on the part of platforms.
That's right. I think, entrepreneurs are faced with a number of fundamental problems that open internet services can help them address. The first problem is fundraising, and tokenized governance systems provide a route towards fundraising through ICOs 2.0. Secondly, they provide a way of getting over the chasm, getting your first users through incentivizing user participation. And then I think the last piece of the equation goes back to platform risk. Big tech succeeds because it benefits from immense network effects derived from all of the user data and relationships that it's hijacked. And if you want to compete with big tech, you yourself need better network effects. Now, token economics are one of the ways you can do that. Another way is by creating non-revocable, trustless APIs and getting other entrepreneurs to build on them and extend out, create a richer ecosystem around your service.
Yeah, I think we saw that. Email is a good example. That's another open protocol where, there was a huge problem, probably peaking in the early 2000s, of spam on the email. And if you go back and look at it, there were news articles saying it's going to destroy email. Very similar to like people talking about bots today on Twitter and Russian bots and all this other kind of talk. What happened with email was, because it was an open protocol, you had lots of capitalistic for-profit companies that created anti-spam companies. So there was I was an entrepreneur back then. It was Brightmail and Postini, and Google ended up buying Postini. But there's a whole rich, probably 50 companies funded by VCs and started by entrepreneurs that tried to solve the anti-spam problem, the spam problem, and they kind of did. It's still an annoyance, but I think most people would say spam has been greatly reduced, and you let the market do that, right? And right now, a company like Twitter just can't do that. They have to solve these problems themselves, because we would never fund, or smart entrepreneurs would never build something on a platform like that, knowing the platform risk. And as a result, they have to do everything themselves, and you don't get the kind of the benefit of the marketplace solving these problems in the way that you did with open protocols. So that's just, I think one thing people are often confused by. I think open protocols is like kumbaya, socialist. Everyone should hold hands and be friends. It's not at all. I think it's the opposite. It's the thing that unlocks kind of self-interested capitalism, which is a very powerful force for solving problems. So you're the founder and chief scientist of DFINITY. You've been working on this for a long time, and I think now with the Tungsten launch, you're approaching kind of you're now opening it up to more people, and in the near future, we'll be launching the kind of production mainnet. Can you tell us, how is DFINITY better than other blockchains? One thing, obviously, is it has a different approach to scaling. Can you talk about that? And then after that, maybe we can talk a little bit about some of the applications you're excited to see built on top.
DFINITY was always technology first. We were fortunate to raise a lot of funds, and we said, we're going to build this NASA for decentralization. We're going to build out a major R&D organization. And we've done that. We've got this absolutely incredible team, research centers in several countries, and we've been, full steam ahead, developing what we believe is a blockchain of the future.
Can you tell us a little bit about the team?
Yeah, so, we've got probably one of the world's strongest cryptography teams within the DFINITY Foundation. And that has been a huge enabler for us with respect to solving certain key problems. So, many years ago, I articulated how things like threshold relay could be used, how we could apply advanced cryptography to create, for example, an unstoppable, unmanipulable stream of random numbers, and how that stream of random numbers could be used to drive a blockchain using something called probabilistic slot consensus. The challenges, though, involve a lot of the supporting infrastructure within the protocol. So you need things like DKGs to set up the cryptography, among many other things. When you drill down into the technicals of a blockchain built the way DFINITY is, it starts to get very complex indeed. And it's probably fair to say that when you move away from a sort of basic proof of work blockchain in the direction of something driven using advanced cryptography, the complexity increases exponentially. So our approach to address that was, just hire all of the world's best talent that we could get and build out our sort of R&D infrastructure, which we've done through, creating research centers and remote teams and so on.
With a blockchain computer like this, there's the cryptography side. There's also, that's the kind of consensus layer. There's also, you have to, for example, have your own, kind of programming environment, kind of networking layer. There's just a whole bunch of different, just similar to to an iPhone, right? There's the chips and the OS and just like a whole bunch of different layers you got to build out, right?
Our approach to this is reductionist. So the internet computer can be thought of as a seamless universe for software. that works in a different way to the software most people are familiar with. For example, persistence happens automatically. You just write code, and you don't need a database or a file system to persist your data. And that's because the Internet computer actually persists the memory pages in which the software runs. So, it was a huge effort. Obviously, you can go as deep as you like. We're very tightly integrated with things like WebAssembly. But, we've created a platform that we think is transformational. And we've aimed to extend the Internet so the Internet becomes the platform upon which we build, as well as the network that connects us all. The Internet computer provides a unique opportunity for entrepreneurs. They can build the next generation of Internet services in the form of open Internet services, and they can leverage all kinds of things you can only get on a blockchain. Tokenization to raise money, tokenization to create incentives for early users, and non-revocable APIs so they can leverage service composability and collaboratively build out the proposition with other entrepreneurs. What kind of things are you looking for in entrepreneurs and projects building on platforms like the Internet computer?
My view is when you have kind of radical new technology, so let's take the mobile phone as an example, you really have, I think you have innovations that are built on top of them that fall into two categories. So you have things which you simply couldn't have done before, and things which you could do before, but now you can do better, okay? And so a mobile phone, what could you simply, like before the mobile phone, like the idea of having a Instagram where you take a photo, or Snapchat, you take a photo and send it to your friend, and like it just wouldn't have made sense on a desktop computer, like you just couldn't have had it. Or Uber and Lyft, right? You needed a mobile phone because you had to have the mobile phone in the car for the driver. So it just simply couldn't have existed. And then you have stuff like Facebook and Twitter, which actually did exist very much on the desktop, right? But they're just better. They're with you all the time. They're, et cetera. So they're sort of, or Amazon for that matter, right? It existed perfectly fine without the phone, but now it's on the phone, and now you can just reach for your phone and buy something, and it's even easier. And so it's similar with blockchain. So there's things that couldn't exist before, and I think some of those are, to me, those are some of the most fascinating things. Like, for example, DAOs, decentralized autonomous organizations, so like MakerDAO and Compound, and there's a bunch of these really interesting new kind of experiments, which are startups that are literally kind of these organizations that are code, and after the entrepreneurs build them and launch them, they're really owned by the community and governed by the community. And it's sort of this really interesting kind of crowdsourcing that we saw applied to Wikipedia for creating information, and to one of the powers of the internet is bringing the crowd together, right? And the crowd can create an encyclopedia. That was an awesome invention last decade. This invention, we're seeing crowds create these kind of virtual organizations that have various functions. That's a brand new idea. It couldn't exist before blockchain. It's really exciting. But there's also, then there's things that we could do before. So we could do social networks before, but now we can do them, or we could do ride sharing marketplaces or things. But now we can do them where the users own part of the network, and where the users govern the network, and the rules for who's platformed and deplatformed and what's acceptable practices and everything else, it can be governed by the community. So I think both are really exciting. I think what tends to happen with new things is the first phase, people kind of rebuild things that already existed in new ways, and it takes time. Like the web is a good example of this. If you look at the 90s, most of the first wave of the web was people just kind of taking things that already existed, like magazines, and putting them on a website. So you go to a hotel website or something, or whatever, New York Times. And then the second wave was, wait, this is more than just internet magazines, right? You can do two-way communication, like YouTube and user-generated stuff. That was the 2000s were the era of YouTube and Facebook and Wikipedia. And so it may be like that with blockchains, like kind of the first wave, you have stable coins and lending platforms and things that are not that radical, but get people kind of used to it. But then over time, you get the really kind of interesting, crazy new stuff. I always love the really interesting, crazy stuff, but it takes time sometimes. But I just think watching that whole evolution is always so exciting when you have this kind of new creative medium upon which developers can build. And they kind of, people are running around and trying to figure out what to do with it. And I think we're about to enter that phase with your launch and just a lot of the innovation generally happening. I think we're about to enter that really creative phase, and that's really exciting.
In a sense, autonomous software was never possible before, so everything that's built using autonomous software is new.
Yeah, then you use the phrase autonomous. We should explain that. I think it's a great phrase. It's not. It's sort of similar to I think it's a better phrase than smart contracts. But the idea is that one of the cool things with blockchains is you write the code, and then the code will continue to persist and run as designed, even if the intentions of the creator change. The code is autonomous in that sense. It's a great word for it, and it really is a new concept. It's why you can trust that software, right? Because you don't have to trust the people behind it. If you write some autonomous software on DFINITY that says I'm only going to have 21 million coins, like the way Bitcoin does, you can trust that the code will keep that commitment, even if Chris Dixon or Dom or someone else becomes evil, right? Like they can't change the rules even if they want to.
One of the most important lessons I've learned in my career as an entrepreneur is that you always want to catch a wave. It's far easier surfing in than paddling out. You don't want to be trying to create a space. You want to be creating something in a space that's rapidly expanding and catch the wave. How do you think this applies to entrepreneurs looking at the decentralization and open computing space today?
We're still early. There's still a ton of opportunity. I think if I had to compare it to, let's say, mobile phones, the most recent kind of massive wave, you had the iPhone came out in 2007, the App Store in 2008, and then probably 2009 through 12 was actually, if you look back, that was the period of Instagram, Uber, Lyft, all of the kind of the huge iPhone apps. I think, DFINITY is trying to be the iPhone. We are pre-iPhone in the blockchain space right now. I believe we're 2005 or 6 to mobile phones, which means that the vast majority, which means 2005 or 6, there was BlackBerry, there was Sidekick, there were a bunch of very successful application developers building mobile apps. But the real action started afterwards, and I think that's where we are now. And I think there's a ton of opportunity. And I agree with you that it's entrepreneurship is so much about catching waves. And there's a lot of waves happening in the world. There's AI, there's the kind of SaaS and cloud and all the other kinds of things. But to me, this is the one that when you kind of look back on every decade in tech, there's kind of one thing that really dominated. And I think this will be the one in this next decade, is my feeling. But obviously, time will tell. But certainly not too late. It's very early, and there's a ton of opportunity. And if you're somebody who's thinking about where to start a company, I think you should really take a hard look at this space.
Yeah, because we're not only changing the platform on what you build, but we're changing what you can build. It's a new kind of platform.
Right. Yeah, I think of it. My friend Balaji Srinivasan has this essay. He calls the idea maze, and he compares entrepreneurship to running through a maze and sort of running into dead ends and finding piles of gold. But where I think the analogy breaks down is what happens in technology is then new kind of enabling infrastructure comes along, which really like unlocks a new section of the maze. And that's what something like the blockchain, like what you guys are going to do, is unlock a whole new maze, and then you get this whole like 5-year period of people running around exploring it. You can still go, and there's plenty of cloud opportunity, but you're running around a maze. A lot of people have run around for the last 10 years, and so you got to be kind of clever and find this little passage over here or something. Whereas here, it's just like a big, fresh, juicy new maze. And so, I think I always like that metaphor and think it's pretty accurate. And yeah, so that's one of the really exciting things about to happen.
And how long do you think this next wave of technology is going to last until it's completely established itself and everyone's building on the open internet?
That's a good question. I think with these really big, I think it's huge. What you're asking is probably the most important question you could argue, it's an important question of the 21st century, is just sort of what's the role of the internet, right? We see this happening in politics, in economics. Like the internet's just this incredibly important invention, and there's sort of two broad views. Like one, I think, is that it's already built out, and now it's kind of like, and this by the way affects like these regulatory questions. Like a lot of people think like, hey, it's built out, there's 4 winners, it's Google, Apple, Facebook, Amazon, whatever, and it's like TV channels, and now the government should come in and regulate them. My view would be it's software. It's much different than hardware, in that software is much more malleable and a much richer design space, and there's a lot more room for entrepreneurship and creativity, and sort of big shifts in paradigms and things like this. And I think we're early in it. I think we're it's like the automobile revolution, and we're in 1915 or something, and like we still got another 80 years of like interesting stuff to happen, or electricity or something. It depends on which historical analogy you prefer, but I think we're really early in it. I think this is the most important blockchains and kind of all of this kind of rich internet infrastructure kind of is the most important thing happening in it, and I think it will take many decades to play out. That said, I think that if you're an entrepreneur, you can have interesting products that reach scale and have good financial outcomes and good, societal outcomes. I think it'll, over the next 5 to 10 years, so more in the near term, but I think it'll also play out longer. Kind of similar to the web or something. Like you had a lot of interesting opportunities in the 90s and 2000s, and you still do, right? It's a huge space.
So how long for a decentralized Uber to overtake Uber?
For these things to really get to scale, I mean, you look at a lot of these internet services today, there are billions of users. If you look at like a WhatsApp, so, it probably takes a decade or something, but along the way, you can have very big, impactful services, right?
Yeah.
And so, we haven't talked yet about the sort of enterprise angle here. How do you see, enterprises, big companies, who want to, get involved here? Like, what do you see their role in the next couple of years?
It's going to be a surprise, and enterprises are going to want to build on the internet. There are a number of reasons. The first is all of them are sick of captive customer games. Today they build on this huge stack with hundreds or thousands of vendors, and all of them are trying to make captive customers. And even if they're not, even if you're using an open source product, it's very easy to get locked in. So that's the first reason that enterprises will prefer to build on the internet. The second one is that the internet computer environment greatly simplifies the process of developing systems. The third one is that these systems that you build are secure by default. So on the internet computer, people create systems and services by uploading these interoperable compute units called software canisters. Software canisters run with all of the security guarantees of smart contracts. The internet computer itself is a tamper-proof environment. You don't need firewalls to protect it, and no one can hack in and find a back door and start subverting your system. So we're seeing an acceleration in the number of major security fails, and hackers are moving on from just stealing PII to actually installing ransomware on people's systems that encrypt all your server instances, and you have to pay Bitcoin or something to decrypt them and get your systems back online. So we've met with a lot of local governments and corporations already that are very interested in finding ways to build tamper-proof systems. Lastly, we actually think many enterprises will start to use the autonomous software features that the internet computer supports. So that means they'll build their own systems in autonomous form and then use governance systems to control the updating of them for security purposes. We also think that a lot of enterprise services like Salesforce will be reinvented in open form. So, we foresee an open internet service that provides Salesforce functionality that is, collaboratively updated and developed by systems integrators and business consultancies around the world, and that open Salesforce will provide a far better deal for most enterprises. So I think enterprise will also shift to using open internet services in the coming years too. Okay, I guess it's time to finish up. Chris, thank you so much for joining our Tungsten launch event. We super look forward to continuing to work with Andreessen Horowitz to build out the internet ecosystem. Thanks again.
So we spent a decent amount of time really chatting a lot about Tungsten today and this particular milestone and moment in time. What I really wanted to do was start our AMA today by chatting a little bit about some of the earlier days for the DFINITY project and some of the work that you did in your past. So from a first question, perhaps you could share a little bit with all of the community members watching around where the inspiration for the internet computer came from.
Well, I've been a long-time nerd, and I started messing around with distributed systems and cryptography back in the late 90s. And, before I got into crypto proper around 2013, I'd created a computer game, an MMO, that scaled to millions of users. And I used a decentralized database called Cassandra, and also created scale-out, horizontally scalable application server to support the interactivity on the platform. And I actually had an algorithm called a weight chain algorithm that enabled some stuff on Cassandra, another thing called Starburst that enabled the application server to work. So, I was already programmed to think in terms of using decentralization to scale out. And then I came across, Bitcoin was on the edge of my sort of consciousness, and I'd read, the Wade Dye's B-Money proposal back in, 1999 or something. Didn't really understand it, but, Bitcoin went through its April pump in 2013 and got my attention. I'm like, wow, man, this is actually working. You can use a fully decentralized network to share a consistent state. It's the world's first stateful decentralized network. And I was absolutely enthralled, as many people were when they first read the Bitcoin white paper. And then by the end of 2013, I was getting frustrated. I was thinking, well, how can I create an altcoin that could be used to support a virtual currency for the games industry? And clearly, you needed much faster finality and scalability and so on. And so I spent much of 2014 exploring traditional Byzantine fault-tolerant consensus protocols, particularly leader-free asynchronous protocols, and proposed this thing called Pebble. And then, of course, the Ethereum project came into being, and that demonstrated something even more interesting, this idea of a blockchain computer. And for me, I saw things, I saw a bigger picture than just smart contracts, and I thought, well, wow, potentially all of humanity's software and services could run off a fast, scalable blockchain computer. And so I started thinking about how that could be done, and I started making early proposals under the DFINITY tag in 2015.
One of the things I also wanted to chat a little bit about is, in your words, where do you believe the project is currently at? We speak a lot around where we would really love to see this project go. And sometimes it might be missed that, this is really a very grand vision. And in some of cases, it might take us years, maybe even decades to accomplish some of these things. So we'd love to kind of get your thoughts on where do you believe the project is at today?
Well, to be clear, over time, there's been a lot of pressure just to launch something and have a internet computer chain. But we've stuck to our guns and said we will only launch something that clearly is the internet computer. So that means we have to be able to support the high levels of performance necessary to run an internet service from what is a blockchain computer, and it has to be able to scale out. And the reason for that is if you can't scale out very quickly, you run out of capacity and everything stops working. And we saw that, for example, with CryptoKitties on Ethereum. Once the capacity was used up, finality went up into the hours. And so, that's why we're called DFINITY. Decentralized infinity means that we need a blockchain computer that can scale out to any capacity as necessary and also, of course, provides the performance. So in order to deliver this, you need to do a lot of technical work. And it's not just engineering. There's also a lot of sort of research and science behind the Internet Computer Project that you don't see when you're just playing with the SDK. And we're going to be revealing more of that progressively. I think a lot of people may already be aware of the original sort of threshold relay and probabilistic slot consensus proposals. And we're still using something like that, although it's more advanced and, as you would imagine, has benefited from several years' work. We've got novel cryptography, all kinds of things inside the project. Now, there's a big difference as well between theory and implementation. So, we proposed threshold relay some time ago. It works very well. However, in order to actually use that within a decentralized network, you need ways of running something called a DKG, or distributed key generation, or in this case, something that might better be called a decentralized key generation protocol to set up the underlying key shares and things like that. And that is extraordinarily complex and so on. So we had to build a different kind of blockchain organization to have any chance of delivering the internet computer vision. And truth be told, we probably underestimated the difficulty initially. But we kept at it. Yeah, we did. We kept at it relentlessly, though, and we've built out this amazing organization. We've got several research centers, a very large team, very large multidisciplinary team. We've got some absolutely outstanding people across everything, all kinds of disciplines. But yeah, of course, also within research and engineering. And I'd say that the organization really began to hit its stride last summer, and we've become a kind of powerhouse. And now we're making amazing progress. So we created these 5 public milestones to launch. The first was copper, and we hit that in November last year. Second was bronze. We hit that at the World Economic Forum in Davos, January this year. This is the third, tungsten, where we're sort of opening up the internet computer incubation to developers, and actually behind the scenes there's a whole load more features that have gone into the network. Some of them not quite there yet, like the ability to fork canisters. The next 2 are sodium, which adds network nervous system governance, autonomy and economics and things like that. And the last one, of course, is mercury. So we've hit the first 3 milestones on time, and I'm hopeful that we're going to hit these 2 following milestones on time too.
So following up on the idea that there is going to be this discrepancy sometimes between theory and implementation, I want to follow up with a quick question that was actually asked by one of the community members during the presentations today. And this one comes from a Safra and Vermeji. And the question was, what do you expect are going to be some of the most exciting / critical next steps in the roadmap? And I know you just spoke of a couple of them, but in your own opinion, what do you think might be some of the most exciting / critical steps that lie ahead for us?
So I think, the community as a whole will be very excited by the network nervous system. It's one of those things that people have often sort of poo-pooed over the years and said it's impossible. And I think people will be very excited to see it actually working. And I think it'll be entertaining too, because everyone will be wondering how this algorithmic governance system is going to churn out decisions on proposals that are submitted. So I think that's going to be fun for everyone, myself included, to watch and play with. Separately, behind the scenes, there's still a lot of interesting technical work being done. So for example, at the moment, the replicas don't make use of the concurrency that's possible when you're running function calls on canisters. And the ultimate evolution of that, where we're heading, is something called deterministic time slicing. And I'm keen to see that done so we can really fully use all of the cores that are on the node machines in the Gen 1 spec, or that are already deployed. And there's also some really exciting new cryptography. So as hopefully people got a sense of, the overall network is controlled by the network nervous system. And the network nervous system actually runs on a dedicated subnet that's extra large. And the network nervous system has a public key, essentially. It's the public key of the subnetwork. Now here's where it gets really cool. The subnetwork, the composition of the subnetwork in terms of what nodes make it up, is controlled through this thing called the registry, which is controlled by the network nervous system. So the architecture of the overall network is dictated by this thing called the registry, and the registry is updated by the network nervous system. And so the network nervous system controls the composition of its own subnetwork, i.e. the network nervous system controls what nodes in the overall internet computer network it's running on. So first of all, the network nervous system, if you like, is able to sort of move around cyberspace and control in a Byzantine fault-tolerant way, using consensus, and control what nodes it's running on. So that's pretty fucking cool. And on top of that, the network nervous system actually has a public key, which is constant for all time. And it's able to maintain this public key even as nodes are swapped in and out of its subnetwork. And that means, that's enabled some very large advances. So for example, if you were a user app, right? Traditionally to validate a blockchain, you have to download all the blocks and so on. That would be impossible with the internet computer because there's too much data and too many transactions. On the internet computer network, all you need to know is the public key of the network nervous system. It's 32 bytes, 256 bits, right? And you can connect to any node in the network, the overall network, and you can ask questions like, I want to interact with this canister, and it can tell you, well, please go and talk to these nodes which are responsible for replicating it. But when it tells you that, it'll give you a little bit of the registry that's been signed by the network nervous system. So as long as you know the 32-byte public key of the network nervous system, you're able to validate that information that's been given to you, right? And of course, that information also gives you the public key of the subnetwork that's hosting the canister you're wanting to talk to. So now you can validate interactions with the subnetwork. So, I mean, that's an example of a big advance. Rather than downloading a whole blockchain, you only need 32 bytes, the 32-byte public key of the network nervous system. But there's even more clever stuff in that you can, that whole system will integrate with the DKG, and if a subnetwork loses for some bizarre reason a vast number of replica nodes, in principle you can rebuild the entire thing. The network nervous system can rebuild the entire subnetwork from a single remaining node, including all the cryptographic key shares, and get the whole thing up and running again. So, people won't see this. I mean, if you're a developer, the subnets are transparent to you, right? I mean, you just upload your canister to the internet computer, and your canister has an ID, and if your canister wants to call another canister's functions, it only needs to know the identity of the other canister and the function signature. The actual structure of the network's transparent. But behind the scenes, there's a whole lot of really clever stuff going on. And so as we go through this year, we're going to be publishing a lot of this, as well as sharing a lot of the, opening a lot of the code.
I did want to kind of mention, so as we've kind of gone through the years at this point, working on the internet computer, there have of course been some project delays. And I would love to kind of get your thoughts, kind of looking back at the time that we've spent getting to this point. What has been surprisingly difficult, as far as implementing? And I think it would be good to give the community a sense of that.
I mean, nobody should underestimate the challenges, the technical challenges involved in building something like the internet computer. It's a very non-trivial project. And I mean, I just talked about some of the custom cryptography involved, and we've got some of the world's best cryptographers, and you really do need, you can't really sort of crowdsource that kind of expertise. And so you need to build a sort of organization that's capable of bringing those kind of people in and then coordinating them. And that's very non-trivial too. So, I think back in 2017, I said that we want to build a NASA for decentralization. And we've been completely true to our word. At the time, there were all these kind of funny memes flying, around, like, rocket ships with the DFINITY logo on the side and so on. Everyone thought it was very funny. But we've been true to our word. I think the bit I certainly underestimated was how long and how difficult it would be to build a NASA for decentralization, like to build out the infrastructure, to create the research centers, to hire people, to create the sub-teams necessary to build out all these different pieces, and there's a lot of them. I mean, and then find ways to coordinate those teams. It's challenging, and and to hire the necessary people. So, we've done that, and I think about a year ago we really began to hit our stride as an organization, and we've become this powerhouse, and we're continuing to expand and get better and better all the time. But it took longer to get to that point than I'd have liked. Whether it could have been done quicker, I don't know.
Got it. So the next question I want to share comes from Sayuri Inada, and she wants to know, what is the data center concentration risk in your view? And I would love to kind of get your thoughts on that, because as we spoke a little bit about the data center model, this for some people might, vary widely compared to what they may have seen before coming out of other projects like the Ethereum Foundation.
So it's a really good question. And I've been involved in blockchain for quite some years, and I'm absolutely obsessed with the underlying science. And we've seen, for example, the problems of centralization in proof of work systems. And, there's even been cases, I think, where, Bitcoin's mining pools have acquired over 51% of the hashing power. There's also another problem in those kind of environments, is that in that you never really know who owns the hashing power. For all you know, it could all be owned by a single party. And that means, if that's the case, the Byzantine fault-tolerant protocol math doesn't work. The same issues with centralization can occur within proof-of-stake networks. So the design of ICP firstly rewards node machines rather than stake. Like every single node machine that's not statistically deviating, that's how we detect faulty behavior or maybe someone running a node that doesn't meet the hardware spec. Every single node machine that's not statistically deviating gets a fixed reward every month, right? So you increase your revenues by running more nodes. Now, the way we get security, the way we create this tamper-proof and the tamper-proof and unstoppable properties of the environment are through composing subnets by selecting nodes from independent data centers, right? It's just not possible for a subnet to have more than one data center, and that's by design. So, it's certainly true that there are some advantages to scale in the sense that the more nodes you run, the more revenues you make. But it's not like proof of work where the ability to generate profits depends very heavily on the cost of electricity. So, in practice, the internet computer network will be far more amenable to professional amateurs than a proof of work network. And the ICP protocol, through its governance system, the network nervous system, inducts data centers, right? So data centers come into the network with a data center ID, and they have to join nodes using that data center ID. And this allows the network nervous system to compose subnets from nodes from independent data centers, which gives you guaranteed decentralization and allows the Byzantine fault-tolerant protocols to work much more effectively and provide far higher levels of, security and liveness than would otherwise be possible.
And this one comes from a Matt Quinn, and it kind of starts diving into a few more questions on the development experience for people who are utilizing the internet computer. And Matt's question was, what can you share at this stage around canister storage cost? I really think ultimately it's going to come down to, for a lot of people, how expensive is it going to be to utilize the internet computer?
So it's a good question. I can't give you a specific answer because economics are coming in with sodium, which is the next milestone. So hopefully you'll have a specific answer at the end of Q3. But what I can say is that the internet computer is designed to be efficient enough and inexpensive enough to use to support hyperscale internet services, things like social media, right? Which is why we're demonstrating CAN-CAN. It is true that the internet computer uses replication for the purposes of Byzantine fault tolerance, and therefore you might assume that the cost of memory will be greater than a traditional project would experience when they're using like Amazon Web Services, content distribution network, and so on. What I'll say is this: we have got some special kinds of subnet coming along. Probably they'll arrive after Mercury that enable sort of allow you to create canisters that have very low cost memory, right? For the purposes of storing, massive amounts of data cheaply. But separately to that, I don't think there's going to be a problem. I'll tell you why. If you actually look at the way the legacy stack maintains data, there's replication everywhere already. First of all, you've got your database, and then, there's the data file, the index file, then you've got the backup snapshots, the log file, and, then you're using memcached because you've got to speed it all up, and then you're almost certainly using a content distribution network to make sure copies of your data exist on the edge of the network. And when you really drill down to it, I don't think that the internet computer uses much more replication at all. But we just embrace replication, which is much more intelligent to deliver a tamper-proof environment that's unstoppable. There's also a native edge architecture, so you don't need a content distribution network. And in fact, we can actually dynamically generate content for you on the edge, in many situations providing far better performance than a traditional internet service will be able to achieve using a hyperscale data center and a content distribution network.
So I'm going to ask one of, I think, the community's most frequently asked questions, and I think it's always worth us spending some time to chat about this and revisit it as we kind of meet our different milestones along the way. And this one is going to come from FC22. And the question is DFINITY going to become fully open sourced once mainnet goes live? And I would love to kind of get your thoughts around not only just the answer to that question of whether or not we will be open sourcing more portions of the internet computer once we kind of get to that public network launch, but I'd also like to get some of your thoughts on whether or not you feel the strategy of not open sourcing all of our content earlier on has been beneficial.
Yeah, good. All good questions. So first of all of the code that implements the ICP protocol will be in the public domain by Mercury. And it has to be in the public domain because otherwise how could anyone verify that it correctly implements the ICP protocol? In addition to that, before we launch, we're going to push vast amounts of technical content out into the public domain. I think I mentioned before that internet computer projects different to most blockchain computer projects in the sense that there's a hell of a lot more novel technical work going on behind the scenes. It's more like a blockchain with 100 white papers kind of thing. We're going to start pushing all of that stuff live, and I think people are going to be really enthralled to see some of the stuff that we've come up with. With respect to open source, we've already started pushing, I think, a lot of the SDK and the canister environment and Motoko implementation live. I think it's using Apache 2 with the LLVM exception. I will say, though, that I'm also interested in new variations on open source, which I sort of call collaborative open source, where you can specify specific projects that can use it, right, to encourage contributions back. So for example, we might say, well, look, we love the Ethereum project. Hey, we will mark this code as usable by the Ethereum project, right? So everyone would have access to it, but it might limit who can use it. And the reason for that, and this sort of impacts on the other part of your question, is why we don't release everything. Part of the reason we don't release everything is we want the ability to make our mistakes in private, and we still sometimes go down one path and back up and go down another path and things like that. And it's only now that we've really stabilized the way we're doing things. But the other piece is that we don't want people just ripping off the code and the systems and just using it to create some ICO ripoff. And there is a sort of tendency sometimes in the blockchain industry to just see this sort of buffet of techniques that are available and sort of cobble them together and then just push something live and say, hey, it's this amazing new thing. And we don't want to feed into that. We want people to develop their own original ways of doing things, and for the internet computer to be its own original thing too. So I think there have been a number of reasons why we've operated in stealth, and I think that period's coming to an end, and people are going to see all this really cool stuff that we've been working on, and we're moving into a phase where we're going to be much more open in the future.
Very exciting. So I want to switch gears to chat a little bit more about just the timing of all of the work that's been going into the DFINITY Foundation and the internet computer more broadly. And I would just love to get your thoughts, and I know you speak to this quite often, but for some of the people who are joining us today, perhaps for the first time, just why now? Why is now a great time to see something like the internet computer brought to market?
For those of you who are a bit older like me, and when remember the 1990s, the internet's lost its mojo. It's dominated by big tech. The stack sucks in a way that takes a lot of the joy out of software development. And if you want to create a new internet service, typically you have to build on the APIs of big tech, which is like building on big, on shifting sands. So, the internet's ripe for a change. It's not just us saying that. And we want to enable this shift where the internet becomes connectivity plus shared computer, and everyone just builds on the public internet. And when that happens, the internet's going to be transformed, because the Internet Computer Platform enables, for example, autonomous open internet services to create non-revocable APIs, which enables something called service composability, so that the whole ecosystem can be built out much more dynamically and collaboratively, enabling more innovation and much greater network effects, which are needed to beat out these monopolistic incumbents who've hijacked everyone's user data and relationships. So that's going to be very exciting, and it's going to enable this sort of new wave of entrepreneurialism and growth and exciting times. And it's also going to change the model, because today, look at LinkedIn. LinkedIn started off espousing the programmable web, right? They shared APIs that allowed other services to incorporate professional profiles from its network into their own services. And that was one of the ways they grew. Like, lots of startups would forward their users to LinkedIn because they thought they could use LinkedIn as a kind of database for professional profiles. Of course, eventually, LinkedIn had everyone's professional profiles. Microsoft bought them, and they decided, well, look, it's much better to be a monopoly. And they revoked everyone's API access. And thousands of startups are absolutely poleaxed by this. And now LinkedIn continues, in the role of a monopoly with its hijacked data, and it just sort of grants a few select services in the big tech oligopoly access to them, like Salesforce. So, innovation, of course, has stopped on LinkedIn, as it has on many other platforms. I mean, how often do you see a change in Google Search, Gmail, eBay? All of these services just stop innovating once they become monopolists. With the Internet Computer Paradigm, it's much easier to create new services because you can build on existing data and relationships. And that's, sharing the user data and relationships that are in your service is one of the ways you're going to succeed, by getting these, leveraging these mutualized network effects and getting people building on top of you, so you can collaboratively build out your ecosystem through service composability. So that's how you succeed and how you beat out monopolistic incumbents. But, there's a sort of pact that's made with the platform there, right? Once you've created permanent APIs that can't be revoked, if you're, say, linked up, and you're the new open social network for professional profiles, and then at some point in the future, your tokenized governance system decides to turn sort of monopolistic, right? It can't really do it because it can't switch off the APIs. It can't even degrade the functionality behind them because the network nervous system will reverse it, which is another topic of conversation. So essentially, you've got to keep on innovating, right? Because if you don't keep on innovating, someone's going to create, open linked up too, and just use the professional profiles that you've already collected through those permanent APIs that you created in order to grow yourself. So it, redefines how the ecosystem works, which I think will be better for everyone. It'll be a huge democratizing force, and it's going to enable much, much higher levels of innovation on the internet.
Thank you again for those answers, Dalman. To close things out, I have one last question for you, and it's essentially, what would you like to see the people who are watching this video to do next? Some of them may be developers, some of them may be DFINITY enthusiasts, community members of different audience types all over the world. In your opinion, kind of what is the next step that they should take to really help us in our journey in trying to reboot the internet?
Well, understand the paradigm, understand the power of it, understand how to leverage that. And there are lots of different ways, right? The internet computer is going to make it much easier to create scalable internet services. But you can also use it for DeFi, enterprise systems, pan-industry systems, just simple websites and so on. But if you're an entrepreneur and you want to create the next wave of open internet services, understand how you can use the paradigm to compete and become successful. So, it could be token economics. You might create an open Uber and give out governance tokens in from your tokenized governance system to early riders and drivers. Understand how you can use the paradigm, and then go and do it. We've got well, not us, but there's an associated venture capital fund called Beacon that focuses on the internet computer projects, but also invest in DeFi. Actually, its first investment was in Compound, which has done very well. But generally speaking, there's a huge amount of capital sitting on the sidelines, ready to go into projects that are building the open internet. I mean, everyone knows that, the current internet is a busted flush. Everyone knows it's controlled by big tech. Everyone's bored of it. Everyone's frustrated that opportunity is being sort of snuffed out by them. And everyone wants to see the open internet succeed. And there's a vast amount of capital. Like when you get a monopolistic system, the thing to remember is that there's always going to be a lot of losers. When you're talking about tech, there's a lot of highly motivated, smart losers, entrepreneurs and investors. And the internet computer is designed to create a way past all of this. And there's an awful lot of VCs out there that will invest in the best projects that assemble really good teams and prototypes and things like that. So, we're looking to support people doing that.
Well, thank you so much, Dominic. This has been wonderful, and we had a really great time today watching all the different presentations, and I'm really excited to start seeing what some of the developers out in the community start doing as it relates to the Tungsten release of the Internet Computer.
Thanks, Mike, and super thanks to everyone attending.
Thank you to everyone for participating in our AMA. Again, we really enjoyed the discussion and appreciated the thoughtful questions from our community.
And now we're giving you the opportunity to experience building on the Internet Computer firsthand. For the first time ever, we are welcoming third-party developers to deploy infinitely scalable apps to the Internet Computer across a network of multiple data centers. With today's Tungsten release of the Internet Computer, we now invite you to apply for early access at DFINITY.org/Tungsten. We will be reviewing applications and extending access to the Tungsten Developer Network on a rolling basis, starting July 1st, 2020.
Thank you to everyone for participating in our Tungsten launch event. There are so many ways for you to get involved and take a leading role in rebooting the internet, and we welcome you to head on over to DFINITY.org to get started. We're looking forward to seeing your creativity and your passion as we return the internet to its free and open roots.